Lexus, Jeep, and Corvette cars are built with precision, power, and cutting-edge engineering. From the robotic welding lines that sculpt their frames to the paint shops that create flawless finishes, every stage is a fusion of technology and craftsmanship. Today, we go inside the factories where luxury meets performance to reveal how these iconic vehicles are designed and brought to life. Inside the sleek, meticulously organized production halls where Lexus vehicles are brought to life, craftsmanship meets cutting-edge automation in one of the most refined automotive manufacturing processes in the world. The journey of a Lexus begins not on the factory floor, but in the minds of engineers, designers, and master craftsmen known as Takumi. These artisans, with decades of experience, help shape the philosophy of quality and precision that defines every Lexus model. Before any physical materials are touched, the vehicle undergoes countless hours of design and digital simulation. Designers model each contour and surface using advanced CAD software, ensuring aerodynamics, aesthetics, and structural integrity are in harmony. Simultaneously, engineers plan out the vehicle's underlying architecture, the chassis, drivetrain, suspension system, and electronic infrastructure, all of which must integrate seamlessly in the final product. Once virtual models and prototypes are validated through digital stress testing and aerodynamic simulation, the blueprint is ready for translation into physical production. Raw materials for Lexus vehicles are sourced globally, but meet stringent internal quality requirements. The main material used in the body is high tensile steel, although aluminum and lightweight composites are becoming increasingly common, especially in performance or hybrid models. Steel coils arrive at the plant in massive rolls and are carefully inspected for surface defects, strength, and elasticity. These coils are then unrolled and fed into precision cutting machines. Automated laser cutters slice the sheets into individual panels, doors, roofs, hoods, and side walls, each shaped with millimeter accuracy. These panels then undergo a series of progressive stamping operations. Gigantic hydraulic presses weighing several hundred tons pound each steel sheet into its designated shape using specialized dies. These dies are meticulously engineered and periodically recalibrated to maintain tolerances as tight as a fraction of a millimeter. During stamping, features like creases, curves, and reinforcement ribs are embedded directly into the metal, contributing both to design and structural integrity. The next stage is body-in-white assembly, where the vehicle's skeletal structure begins to take shape. Robotic arms equipped with weld guns perform thousands of spot welds per car, joining the stamped panels together into a rigid, seamless shell. Lexus factories often employ laser welding for specific areas like roof joints or pillars, achieving a cleaner finish and stronger bonds than traditional methods. A select group of highly trained technicians also perform manual welding in hard-to-reach areas, ensuring consistency across every build. Cameras and sensors continuously monitor the alignment of every panel to detect even the smallest deviations in fit or finish. With the raw body now assembled, it enters the paint shop, a controlled environment with extremely high cleanliness standards. Prior to painting, the body is submerged in an electrodeposition tank, where it's coated with a rust-inhibiting primer using an electric charge to bind the molecules to the steel. This anti-corrosion step is essential for longevity. After that, the car body passes through an automated sanding and cleaning line to prepare the surface for color application. Paint is applied in multiple coats: primer, base coat, and clear coat, using robot sprayers that mimic human wrist movements for a natural, even finish. Each paint layer is flash dried in curing ovens set to precise temperatures, and between each layer, the body is inspected under UV and white light to catch any inconsistencies or inclusions. Lexus offers a range of colors, but each hue is carefully developed to interact with lighting and body shape in a specific way. The final clear coat is cured in a high-temperature bake oven, after which the body is cooled slowly to prevent microcracking or warping. As the painted shell makes its way to general assembly, the mechanical heart of the Lexus is being prepared in parallel. Engine blocks, transmissions, hybrid drive units, and other powertrain components are either produced in-house or arrive from specialized manufacturing partners. These components undergo their own precision machining processes. Crankshafts are ground to micron-level smoothness. Cylinder heads are pressure tested for leaks, and valve trains are assembled under cleanroom conditions to prevent particulate contamination. Every engine is hot tested with synthetic oil and run on a bench to simulate driving conditions, ensuring it meets Lexus's strict vibration, noise, and torque standards. In the chassis line, the painted body is now mounted onto its corresponding suspension and drivetrain system. This is performed on synchronized conveyor lines where the body and the chassis meet in a process called marriage. Sophisticated vision systems and robotic arms align the two structures with such precision that no manual corrections are necessary. Once married, the vehicle receives its fuel system, braking components, and exhaust system, each installed by a combination of robots and skilled technicians. Wiring harnesses, which can include several kilometers of cable, are laid out using templates and fixed in place by specialized machines. These harnesses connect the vehicle's electronic control units, sensors, infotainment systems, and safety devices. Interior assembly follows, beginning with the installation of insulation, sound deadening mats, and undercarpet padding. Lexus places a high priority on NVH, noise, vibration, and harshness. So every panel is fitted with dampening materials to ensure a quiet ride. Seats are assembled in a separate clean area and installed using automated arms with torque sensors that ensure fasteners are neither under nor over-tightened. Dashboard modules, which include HVAC controls, infotainment screens, and digital displays, are pre-assembled on sidelines and inserted into the cabin in one synchronized motion. The steering column is calibrated for tilt and telescopic movement and connected to electronic steering systems, while airbags and sensors are fitted with strict adherence to safety protocols. Once the interior and exterior trim are installed, including lighting assemblies, mirrors, grills, and body moldings, the vehicle proceeds to the fluid fill area. Here, robotic nozzles inject the precise quantities of engine oil, brake fluid, coolant, transmission fluid, and refrigerant for the air conditioning system. Each fill is tracked by weight and volume sensors to guarantee consistency. After this, the car undergoes wheel mounting and torque checking using specialized tools that record every bolt's torque signature to ensure they meet Lexus's specifications. Now fully assembled, the car enters the dynamic test stage. Every Lexus is driven on a test track or rolling road that simulates real-world driving conditions. During this phase, technicians listen for abnormal noises, feel for vibrations, and monitor electronic systems to confirm everything operates within design parameters. Brake response, suspension feel, steering feedback, and drivetrain behavior are all evaluated in real time. Vehicles equipped with advanced driver assist systems undergo calibration and functional checks using target boards and optical sensors. If any anomaly is detected, the car is flagged and routed to a correction station for adjustments or part replacement. Quality assurance is not a single checkpoint, but a continuous presence throughout the assembly process. Hundreds of sensors, scanners, and cameras monitor every assembly station. Torque tools are networked into the plant's central server to ensure bolts are always fastened correctly. Paint is checked not only by human inspectors, but also by multi-angle robotic sensors that detect flaws invisible to the human eye. Final inspection is carried out by Takumi masters who evaluate the vehicle's tactile and visual quality. They look at panel gaps, feel the texture of materials, and assess the overall aesthetic with a level of scrutiny that only comes with decades of experience. Once cleared for shipping, the car is fitted with temporary protective coverings on high-contact surfaces like the hood, mirrors, and interior trim. It then moves to the logistics center where it's sorted by destination. Lexus uses a just-in-time distribution system to minimize storage time and ensure each vehicle arrives at the dealership in showroom condition. Transport is typically handled via rail or enclosed trucks, depending on the destination. Some markets require additional port processing, such as compliance with regional emission standards or language-specific infotainment updates before the vehicles are delivered to showrooms. What truly sets Lexus apart, however, is not just its meticulous production, but the ethos that underpins it. The Lexus production system, derived from the famed Toyota production system, emphasizes continuous improvement, waste reduction, and human-centered manufacturing. Workers at every level are encouraged to stop the line if they notice an abnormality, a culture known as jidoka or built-in quality. Every process is subject to kaizen or incremental improvement, meaning the manufacturing floor is in a constant state of optimization. Even the robots are not fixed assets. Their programming is continuously updated based on feedback from human workers. This seamless blend of human mastery and robotic precision results in a vehicle that embodies both technological advancement and handcrafted excellence. From the silent glide of the paint robots to the calm concentration of a Takumi applying finishing touches to a wooden inlay, each Lexus carries within it the philosophy of omotenashi, a spirit of hospitality and attention to detail that transcends machinery. In a world increasingly dominated by automation, the Lexus factory is a compelling reminder that the future of manufacturing lies not in replacing the human touch, but in elevating it. Inside the rugged and powerful world of Jeep manufacturing, toughness isn't just a design principle. It's embedded in every step of the industrial process. Jeep vehicles, renowned for their off-road capabilities and iconic status, are built in factories that combine high-strength materials, advanced robotics, and decades of engineering experience to produce vehicles capable of handling everything from city streets to extreme terrain. The story of how a Jeep comes to life inside a factory is a narrative of precision, durability, and relentless testing, all shaped by a legacy that dates back to World War II. It all began in the early 1940s, when the US military needed a lightweight, go-anywhere reconnaissance vehicle. What followed was the birth of the Willys MB, the direct predecessor to the Jeep. Over the decades, the brand evolved from a military utility vehicle to a global symbol of adventure, strength, and freedom. Today, Jeep models like the Wrangler, Grand Cherokee, and Gladiator are produced in high-tech manufacturing facilities that carry forward the DNA of the original while incorporating the very latest in automotive production technology. The process begins long before the first bolt is tightened. It starts with engineering teams who define the specifications of each new model based on performance expectations, off-road capability requirements, safety standards, and customer feedback. Computer-aided design and simulation tools help model every component, from the ladder frame chassis of a Wrangler to the unibody structure of a Grand Cherokee, ensuring each part is strong, lightweight, and optimized for performance. Crash simulations, airflow analysis, and even water fording simulations are run digitally, months before any physical part is made. Once the vehicle design is finalized, raw material procurement begins. Jeep factories rely heavily on high-strength steel alloys, aluminum, and composite plastics. These materials arrive at the plant as massive coils or billets and are rigorously inspected for imperfections. Each batch is traceable, meaning any material used in a Jeep can be tracked back to its origin. This ensures consistency, compliance with safety regulations, and accountability. These raw materials first enter the stamping plant, where they are transformed into body panels and frame components. Enormous stamping presses, some standing 3 stories tall, shape the steel using dies that apply thousands of tons of pressure. Each panel must conform to strict tolerances, as even a 1mm misalignment could throw off the entire vehicle structure. Jeep vehicles, especially models designed for off-road use, require thicker and more robust structural reinforcements than many consumer vehicles. This means extra ribbing is built into the dies, and additional pass-throughs in the press lines ensure structural rigidity in critical load-bearing areas like wheel arches and suspension mounts. The formed body panels are then routed to the body shop, where robotic welding arms assemble them into the vehicle's skeleton. For a Jeep Wrangler, this means bringing together the floor pan, sidewalls, roof structure, and rear panels into a boxy, trail-ready frame. The welds must be strong and consistent, especially for a vehicle expected to endure torsional flex and harsh impacts off-road. Jeep factories use a mix of MIG welding, laser welding, and resistant spot welding. Over 5,000 welds go into each body, with robots performing the majority, while human technicians focus on quality critical joints or hard-to-reach spots. A unique aspect of Jeep production, especially for the Wrangler, is the modularity of the body. Doors, roofs, and windshields are designed to be removable, which adds complexity during assembly. Tolerances must be tighter because customers expect parts to detach and reattach easily, without leaks or vibrations. This means extensive calibration and fit testing is built into the body shop workflow. Every door frame and roof panel is test fitted and adjusted using pneumatic tools and laser measuring systems to ensure flawless alignment. Once the skeletal body is complete, it heads to the paint shop, one of the most technologically advanced areas in the plant. The vehicle first undergoes a thorough cleaning and surface preparation. This includes a dip in a phosphate bath to clean off oils and contaminants, followed by electrocoating, where the vehicle is submerged in a tank and an electrical current bonds an anti-corrosion primer to every surface, including hidden cavities. After drying, the vehicle enters the painting booths. Here, robots apply multiple coats of paint, primer, color, and clear in a dust-free environment. Jeep offers bold colors inspired by nature and adventure, such as Sarge Green or Firecracker Red, each mixed with precise pigment ratios and applied with fluidic nozzles that mimic human spray techniques. Each coat is oven-cured to form a resilient finish, capable of withstanding UV exposure, mud, salt, and rocks kicked up from the trail. After painting, the body shell enters the general assembly area, the heart of the production line. This is where the Jeep transforms from a metal shell into a fully equipped vehicle. It begins with insulation, sound-deadening materials, and sealants applied inside the cabin. For Jeep models, this includes water-resistant treatments, as many vehicles are designed for water fording. Door seals and body gaskets must meet strict compression and durability standards. Wiring harnesses are installed next, and these are more complex than ever. Modern Jeeps feature hundreds of sensors, infotainment systems, off-road driving modes, and safety technology. These harnesses are laid in place using programmable placement arms and secured with clips, zip ties, and heat shrink tubing, depending on the location and exposure to moisture or vibration. Next comes the marriage of the chassis and powertrain with the painted body. For body-on-frame vehicles like the Wrangler and Gladiator, the heavy-duty steel frame is assembled separately, including solid axles, coil or leaf springs, differentials, skid plates, and suspension arms. The frame is then bolted to the body using hydraulic lifts and torque tools that ensure each fastener meets exact tension values. For unibody models, like the Cherokee or Compass, this integration happens earlier in the line, with subframes bolted directly to the structure. Jeep powertrains are built for torque, durability, and versatility. Engines such as the Pentastar 5.6, the Hurricane turbocharged inline-4, or diesel options are assembled in parallel engine plants where they undergo machining, balancing, and dyno testing. Each engine is hot tested for leaks, performance, and emissions compliance. Transmissions, white, whether manual, automatic, or dual clutch, are mated to the engine on a subline, forming the complete drivetrain assembly. This unit is then raised into the chassis using synchronized lifts and installed with precision fasteners that ensure alignment and vibration isolation. Drivetrain components are connected next. Drive shafts, transfer cases, and locking differentials, all essential for Jeep's off-road performance, are installed and calibrated. Specialized torque sensors verify that each fastener is within spec, and camera systems double-check routing and connections. Jeep's 4x4 systems require precise calibration, especially when electronic terrain management systems are used. These allow the driver to switch between mud, sand, snow, and rock crawling modes, adjusting throttle mapping, gear ratios, and traction control accordingly. Now, the vehicle moves into interior and exterior trim assembly. Seats, dashboards, consoles, and trim panels are installed by teams working in pods, with each station responsible for fit, function, and finish. For premium models like the Grand Cherokee Summit, this includes hand-stitched leather, real wood accents, and digital clusters that must be pixel perfect. Each infotainment screen is tested for dead pixels and software integrity before leaving the station. Rugged models like the Wrangler Rubicon get special features such as washable floor mats, reinforced roll bars, and waterproof switches. Exterior components like grills, bumpers, lighting assemblies, and badging are added in tandem, with a final alignment check to ensure symmetry and fit. Next, the vehicle proceeds to the fluid fill station, where all vital systems are charged with fluids: motor oil, transmission fluid, differential gear oil, coolant, brake fluid, power steering fluid, and refrigerant. Each fluid fill is done robotically, with flow meters and digital monitoring to verify quantities and eliminate the risk of leaks. Finally, the Jeep enters a rigorous quality and testing phase. This begins with a rolling road test, where the vehicle is driven on dynamometers to test drivetrain performance, braking, steering, and electronic controls. Special off-road simulations are run to verify that lockers engage, hill descent controls activate, and all-wheel drive functions correctly. Vehicles are then driven over test tracks with potholes, speed bumps, and articulation ramps to simulate real-world terrain. Water intrusion tests involve spraying the vehicle at high pressure from multiple angles to ensure seals hold. Each Jeep undergoes a final inspection by trained quality specialists who look at paint finish, interior trim, panel gaps, and feel for any mechanical irregularities. Light tunnels and tactile checks help identify imperfections. Every vehicle is barcoded and logged, with full traceability of every component and test result. Once approved, the vehicles are sent to the logistics center. Some are loaded onto rail cars for cross-country shipment, while others are driven onto enclosed trucks for dealer delivery. Jeeps destined for export are often protected with shrink wrap, and some may be reconfigured with market-specific hardware or software updates before final delivery. Inside the meticulously engineered world of Corvette production, speed, performance, and precision craftsmanship converge inside one of the most specialized automotive manufacturing facilities in the world, the General Motors Bowling Green Assembly Plant in Kentucky. This is the only place on Earth where every Corvette is built, from the very first weld to the final roar of the engine. From hand-built V8 power plants to aerospace-grade composite panels, the modern Corvette is the result of decades of performance heritage married to cutting-edge manufacturing science. The process of building one of America's most iconic sports cars isn't just an industrial operation. It's an orchestrated symphony of engineering, robotics, skilled labor, and quality control, working together to create a machine that is capable of competing with the best exotic vehicles on the planet. The Corvette's legacy stretches back to 1953, when the very first model rolled off a makeshift production line in Flint, Michigan. It was a lightweight, fiberglass-bodied roadster powered by a modest inline-six engine, but that humble beginning sparked a revolution. Over the decades, the Corvette evolved, gaining V8 engines, refined suspensions, racing pedigree, and global prestige. In 2020, the Corvette took its biggest leap yet. The C8 generation transitioned to a mid-engine layout, fundamentally altering how the car is designed, built, and performs. This change not only shifted the car's balance and handling characteristics, but required a complete rethinking of the manufacturing process. The factory itself was overhauled to accommodate the new architecture, including the installation of hundreds of millions of dollars worth of robotics and tooling, all to support the Corvette's transformation into a true supercar. The process begins with the core of the vehicle, the chassis and structural frame. The C8 Corvette uses a bespoke aluminum space frame that provides high torsional rigidity with relatively low weight. The aluminum arrives at the factory in billet or coil form, sourced from certified suppliers meeting strict metallurgical standards. Before fabrication, each aluminum piece is scanned for flaws using non-destructive testing methods, such as ultrasonic or X-ray analysis. Once cleared, the aluminum is extruded, stamped, or hydroformed into the necessary components, including rocker beams, cross members, and crash structures. The hydroforming process is particularly fascinating. In this technique, aluminum tubes are placed into dies and then expanded into their final shape using pressurized hydraulic fluid. This allows for complex, hollow parts with superior strength-to-weight ratios, ideal for the Corvette's safety and performance needs. After forming, robotic systems with high-precision weld arms begin assembling the frame using a combination of MIG welding, laser welding, and structural adhesives. The fully assembled frame is placed on a rotating jig that allows for 360-degree access, ensuring welds are placed with micron-level precision. Each frame is scanned with a 3D vision system to verify all dimensions before moving to the next station. While the frame is coming together, another crucial part of the Corvette, the body panels, is being fabricated. Unlike most mass-market vehicles, the Corvette's skin is made from lightweight composites, including fiberglass reinforced plastics, carbon fiber, and sheet-molded compounds. These materials provide strength and shape without adding the bulk of traditional steel panels. Fiberglass panels are formed through a process called compression molding, where pre-cut fiberglass mats are placed in heated molds and compressed under extreme pressure with resin. Carbon fiber parts, such as the front splitter or roof panels in high-performance trims, are layered by hand or through automated layup machines, then cured in industrial autoclaves that apply heat and vacuum pressure to harden the epoxy resin binding the fibers. Each panel is hand-inspected for voids, fiber alignment, and surface imperfections before heading to paint. Since composites expand and contract differently than metal, Corvette panels require their own specialized painting process. The painted body panels must not only match each other perfectly, but must maintain color integrity over time, even under high UV exposure and heat. Paint robots apply multiple coats: primer, base, metallic or pearl layer, and clear coat, with each step oven cured. Color matching is so critical that Corvette offers customers a paint inspection under natural light to approve their vehicle's finish before delivery. Back at the main assembly line, the aluminum chassis and painted body panels are now ready to come together. The chassis first moves through the marriage process, where it is combined with the suspension, brakes, steering components, and cooling systems. Each suspension arm is installed using robotic torque tools that log every bolt's torque value in a centralized quality database. Corvette's advanced suspension options, including magnetic ride control and adjustable dampers, are calibrated at this stage using diagnostic computers connected to the vehicle's internal CAN bus system. The next major milestone is the installation of the powertrain. Unlike most vehicles, Corvette engines are not installed en masse by an overhead crane or conveyor. Instead, each engine is mounted into a subframe along with the dual clutch transaxle and rear differential. Then the entire unit is raised into the car from below using an automated lift platform. This method, called a cradle install, allows for better alignment and reduces stress on the vehicle's structure. The C8 Corvette uses a rear mid-engine layout, so the mounting process is complex and requires exact alignment of multiple mounts, fluid lines, wiring harnesses, and cooling ducts. The engine itself is built at the Performance Build Center, a special clean room inside the Bowling Green factory where trained technicians hand-assemble each V8 by hand. In fact, Corvette customers can even pay to participate in this process through the Engine Build Experience program. Every engine is constructed using torque-to-yield fasteners, precision-balanced rotating assemblies, and individually tested components. Pistons are matched by weight within grams. Valve lash is measured and adjusted to strict tolerances. Each finished LT2 or LT6 engine is then tested using a hot run bench that simulates real-world driving conditions. Oil pressure, combustion noise, RPM range, and emissions are all logged before the engine is certified for installation. Once the powertrain is integrated, the Corvette proceeds to the electrical and interior assembly areas. Wiring harnesses are installed first, snaked through the monocoque chassis and connected to control modules. The vehicle's electronic brain includes over 24 modules, managing everything from traction control to wireless connectivity. Technicians perform continuity and resistance tests at every connection point. After electrical setup, the interior components are added, including carbon fiber dash inserts, premium leather seats, and customizable infotainment systems. Materials for the cabin are cut and sewn on-site with real aluminum, suede, and leather used extensively. Each interior is installed by a specialized team that ensures tight fit and finish across every seam, panel, and switch. As the Corvette approaches final assembly, exterior panels are now fitted to the car. Because composite panels are more flexible than metal, special alignment jigs are used to ensure consistent panel gaps and flush mounts. Each door, hood, and hatch is tested for smooth operation. At this stage, every Corvette begins to resemble its final form, with aggressive aerodynamic lines, wide fenders, and the unmistakable mid-engine proportions that define the C8 platform. With the vehicle now complete, it moves into the final inspection and validation zone. Here, a full suite of dynamic tests is run. The Corvette is placed on a 4-post shaker rig to simulate road vibrations and detect any abnormal noises. It is then moved onto a rolling dynamometer where the vehicle is driven up to highway speeds. While engineers test shifting behavior, throttle response, cooling system efficiency, and stability controls. Brake systems are tested for fade resistance and ABS performance. High-speed fans simulate airflow to confirm cooling under load. After dynamic testing, each Corvette is subjected to a water test. High-pressure jets are sprayed from all angles to confirm weather seals and water resistance. A separate light tunnel is used for a full-body visual inspection under high-lux lighting that reveals imperfections in paint, fit, or finish. Each vehicle is signed off by a final inspector who performs a checklist of over 100 items, ranging from alignment and cosmetic perfection to software version checks and VIN registration. If everything passes, the car is moved to the shipping prep area. Protective wrapping is applied to sensitive areas like the nose, mirrors, and roof. Final fluids are topped off, the battery is charged, and tire pressures are adjusted. Corvettes destined for US dealers are loaded onto enclosed trailers, while international units are prepared for shipping in climate-controlled containers. The factory offers a museum delivery program, allowing customers to pick up their vehicle in person at the National Corvette Museum across the street. An experience that includes a factory tour and photo documentation of their car's birth. From molten aluminum to a roaring mid-engine sports car, every Corvette that rolls off the line is a symbol of American engineering at its most passionate and refined. The attention to detail, the fusion of handmade assembly with robotic precision, and the obsessive quality control processes all contribute to a vehicle that isn't just built, it's crafted. For over 70 years, the Corvette has stood as an icon of speed and innovation, and inside the Bowling Green factory, that legacy is forged daily in metal, carbon fiber, and thunder. To understand the making of a Honda Civic, we must start long before the wheels ever touch asphalt. At the very genesis of the production journey, the press shop. It is here, in a thunderous hall lined with towering metal-forming presses, that raw coils of rolled steel arrive from trusted suppliers. These steel coils, typically delivered on massive trucks or freight trains, are carefully quality checked for thickness, tensile strength, and surface consistency. Technicians inspect the incoming steel with precise ultrasonic and magnetic sensors, looking for any hidden flaws that might affect structural integrity. Once verified, the steel coils are loaded onto an unwinding line and fed into massive blanking presses, machines that slice sheets to exact dimensions for body panel stamping. This stage is not about shape yet. It's about preparing the right size of metal blanks that will later be contoured into the Civic's recognizable exterior components. Each blank is fed robotically into a deep draw stamping press, some of which exert more than 2,000 tons of force in a single downstroke. These presses contain die sets, essentially giant molds machined to micrometer tolerances, which shape the flat blanks into complex three-dimensional parts: doors, hoods, quarter panels, floor pans, and roof skins. The stamping process is both violent and elegant. With each press cycle, a blank disappears between the dies, emerging seconds later with ridges, folds, and curves now embossed into the once flat steel. Robotic arms then transfer these parts to stacking racks with vacuum grippers, organizing them for their next destination, the body shop. If the press shop is the forge, the body shop is the sculpture studio. It's here that the Civic begins to take on its distinctive silhouette. Using a mix of robotic welders, jigs, and human technicians, the various stamped body panels are aligned with incredible precision. Fractions of a millimeter make all the difference in structural rigidity and door fitment. The underbody is constructed first. Floor pan, frame rails, and cross members are robotically welded together in massive fixtures that hold them square. These sub-assemblies are then mated with the upper body structure, including the firewall, roof bow, and side panels. The process of joining these panels together is an art form in itself. Honda uses a combination of spot welding, where copper-tipped electrodes pass current through panels to fuse them, and laser welding, which offers even greater strength and less distortion. Each Civic contains thousands of spot welds, each one measured by inline sensors for penetration, pressure, and temperature. In certain areas, structural adhesives are also applied robotically before parts are pressed together, increasing torsional stiffness and reducing vibration. As the body shell, now called the body in white, progresses through the line, it moves through various stations where more components are added: inner reinforcements, mounting brackets, and crash structure members. Robots ensure these parts are always placed in precisely the same position on every vehicle. The body is then passed through a computerized vision inspection system, which scans it in real time for dimensional conformity. If anything is off, even by a millimeter, it is flagged and corrected immediately. With the body in white completed, the Civic now advances to one of the most critical and carefully controlled areas in the factory, the paint shop. Before any color can be applied, the raw steel must be prepared with a meticulous cleansing process. The car shell is first subjected to a multi-stage bath sequence in giant dip tanks that use alkaline detergents to remove oils, dust, and microscopic particles left over from stamping and welding. The shell is rotated robotically through each tank, allowing it to be completely submerged and ensuring even coverage across all surfaces, both exterior and hidden interior cavities. After cleaning, the body enters an e-coat bath, short for electrophoretic deposition coating. In this step, the shell is electrically charged and dipped into a tank filled with a water-based primer containing corrosion-inhibiting particles. The electrical charge causes the primer particles to be attracted and evenly bonded to the body's surface. This layer not only improves paint adhesion, but provides crucial rust protection, especially in inner cavities that are hard to reach with spray guns. Once the e-coat is cured in an oven at around 180 degrees Celsius, the Civic moves into the primer application booth, where robotic arms spray a base primer coat across the shell. This step evens out the surface texture and prepares it for color paint. Following a short curing phase, the vehicle is moved into the color booth, a climate-controlled, dust-free chamber where the final paint coat is applied. Each Civic model has its own unique paint codes, which are carefully loaded into robotic arms that spray layer upon layer of base coat and clear coat in a highly choreographed dance. The painting process is arguably one of the most mesmerizing stages to witness. 12-axis robotic arms glide effortlessly around the car body, their movements pre-programmed down to the millisecond, ensuring consistent paint thickness and flawless coverage. The color coat is followed immediately by a layer of clear coat, which adds depth and gloss while protecting the finish from UV light and environmental damage. After curing in a second oven for up to 40 minutes, the freshly painted Civic body emerges gleaming, but still empty. Just a hollow shell with no glass, no engine, no wheels. That's about to change. The next phase, phases, is the trim and chassis marriage line, where the Civic's raw body begins to transform into a fully outfitted vehicle. This is where thousands of individual parts, from wiring harnesses to dashboard assemblies to seatbelt retractors, are installed piece by piece, each in a strictly orchestrated order that has been optimized for both ergonomic efficiency and production speed. Before any of that happens, however, the body must be precisely prepared for the installation of glass. Robots apply urethane adhesive beads around the front and rear window openings, and then suction-equipped robotic arms carefully position and press fit the windshields and back glass into place. Smaller fixed windows are installed similarly. These adhesives not only secure the glass, but also provide structural rigidity and watertight sealing. Inside the cabin, the assembly line team begins installing sound deadening mats, interior wiring looms, dashboard subframes, HVAC ducting, and insulation panels. Every cable must be routed correctly through predefined paths using color-coded guides and clips to avoid interference or rattling. Robots and technicians work side by side. Robots handling repetitive or awkward tasks such as bolting down seat frames or placing door wiring clips, while humans complete more dexterous jobs like feeding dashboard harnesses through tight spaces. In a parallel part of the factory, just as precise and choreographed as the main body line, the powertrain assembly line is busy bringing together the mechanical heart of the Honda Civic. Here, in a series of carefully timed workstations, the engine block, cast from aluminum alloy at an off-site foundry, is delivered for the beginning of what will become a highly intricate construction process. The raw engine block, a silvery rectangular core with machined bores and passages, is first mounted to an adjustable rotating stand that allows technicians and robots to access all angles of the component with ease. Technicians begin by installing the crankshaft, main bearings, and connecting rods, each component measured to precise tolerances using torque wrenches and digital sensors. The pistons are inserted and aligned with the cylinders, lubricated and checked for correct seating before the cylinder head is mounted and bolted down in a strict torque sequence. Fuel injectors, spark plugs, oil pans, gaskets, and camshafts are all installed in sequence. Robotic arms place timing chains or belts, set cam phasing, and verify timing alignment using vision inspection systems that reference QR codes and part markings. Once complete, each engine goes through a cold test station where sensors check oil circulation, compression ratios, and component tolerances without actually firing the engine. If the unit passes, it continues down the line to be joined with the transmission, either a continuously variable transmission, 6-speed manual, or in some markets, a traditional automatic. These transmissions arrive from specialized Honda transmission plants and are pre-assembled with clutches, gears, and hydraulic valve bodies already in place. The marriage of engine and transmission is done with the help of alignment jigs and torque-monitored bolt drivers to ensure perfect balance and alignment. This combined powertrain module is then sent via automated guided vehicle to the chassis line, where other sub-assemblies, such as the front subframe, suspension arms, steering rack, and exhaust system, are already being built up. In this stage, the Civic's front and rear subframes are assembled separately, each housing the relevant suspension geometry, control arms, sway bars, and dampers. These are pre-torqued and inspected before being mated to the powertrain and chassis cradle. Once this fully assembled underbody unit is complete, it moves via overhead conveyor to the marriage station, a dramatic intersection of the trim line and the chassis line. The painted body shell, with dashboard and interior partially installed, is suspended above the cradle. Slowly, the two converge. Using laser guidance and a complex hydraulic lift system, the car body is lowered onto the powertrain module with millimeter precision. Specialized guide pins ensure perfect alignment, and robots immediately begin bolting the chassis and body together at multiple mounting points. This process, known as the body drop or marriage, represents one of the most pivotal points in the Civic's construction. In just a few minutes, the car transitions from a hollow shell to a complete vehicle with drivetrain, suspension, and steering components now integrated. From here, the assembly line continues with intense precision as the Civic begins to come alive, inch by inch. The next station involves connecting electrical harnesses and fluid lines. Large modular connectors are snapped into place, linking the vehicle's main computer systems, ECU, sensors, transmission control, and lighting. Brake lines, fuel hoses, coolant pipes, and air conditioning refrigerant lines are connected with quick coupling fittings that are color-coded and pressure-tested for leaks. Robots insert and fasten fuel tanks underneath the chassis, followed by heat shields and underbody panels that protect the car's systems from road debris and temperature extremes. Meanwhile, technicians inside the vehicle are installing the instrument panel, infotainment system, airbag modules, and steering wheel. The center console and infotainment head unit are test-fired on the spot, using a temporary power source to ensure all touchscreens, audio systems, and onboard diagnostics are functional. Seats arrive pre-assembled from a separate supplier and are robotically positioned, bolted down with monitored torque drivers, and electrically connected for airbag and heater functions. Simultaneously, the doors, which were removed earlier in the process to improve access during interior assembly, are now reattached by a series of 6-axis robots. These machines lift the doors from their carriers, align them to body datum points, and bolt them onto reinforced hinges with a precision that's been pre-calibrated using 3D body scans taken earlier. Technicians then install seals, trim pieces, weather stripping, and window regulators before the power windows are connected and tested electronically. Next comes the installation of exterior lighting. Headlamps and taillights are snapped into place with molded brackets, fastened with screws and bolts, and connected via waterproof electrical connectors. Each light module is briefly illuminated to confirm functionality and correct alignment. The front grille, bumper fascias, and underbonnet components, such as the air intake ducting, battery, and fuse boxes, are added next. Every step in this stage is monitored in real time by a central production server that tracks torque readings, scan codes, and pass/fail diagnostics from every tool on the line. With nearly all physical components in place, the Civic is almost complete, but not quite ready to leave the line. Next, the wheels and tires are installed. Tires arrive from Honda's tire supplier, already mounted and balanced on alloy wheels. They are indexed and attached to the hub assemblies using robotic wheel guns calibrated to apply the exact torque specification for each lug nut. These specs vary depending on wheel size, market, and drivetrain layout. An automated alignment station immediately follows, where high-speed cameras and laser sensors measure and adjust toe, camber, and caster angles on all 4 wheels. These adjustments are performed automatically by robotic arms that adjust the suspension linkages without human input. The engine is now ready for its first breath of life. The car is filled with all necessary operational fluids: engine oil, transmission fluid, coolant, windshield washer fluid, brake fluid, and refrigerant. These fluids are dispensed using automated boom systems that identify the vehicle model via RFID tags and fill to precise volumes using flow sensors. Then, the Civic moves into the initial startup bay, where for the first time, its ignition is triggered. An onboard computer runs a rapid series of checks on fuel pressure, ignition timing, emission systems, and electrical networks. If any error code is flagged, the vehicle is diverted for diagnostics. If everything checks out, the Civic proceeds. Following startup, the vehicle undergoes a dynamic rolling test on a set of inline dynamometers. The car's wheels are driven at varying speeds while technicians monitor acceleration, braking, gear shifting, and engine response. Noise, vibration, and harshness levels are recorded using microphones and vibration sensors in key areas. The vehicle's radar, sonar, and camera-based safety systems, like lane keeping assist and adaptive cruise control, are also calibrated using test targets and moving objects. Even the horn and windshield wipers are tested as part of this comprehensive validation. Once mechanical systems are signed off, the Civic advances to the water test booth, an enclosed tunnel fitted with high-pressure nozzles simulating rain and storm conditions. The car is sprayed for several minutes from all angles to ensure no water leaks into the cabin or trunk. Any intrusion, however slight, results in the vehicle being pulled for resealing and retesting. After the water test, the Civic passes through the final inspection bay. Here, a team of trained inspectors examine every surface of the car under bright, full-spectrum lighting to detect paint imperfections, panel misalignments, or blemishes. Doors, hoods, and trunks are opened and closed repeatedly to confirm proper fit and latch operation. Interior materials are checked for stitching quality, switch function, and material alignment. Even the scent of the cabin is evaluated to ensure consistency with Honda's brand standards. Once it clears final inspection, the Civic is driven briefly to a short holding area where any software updates are flashed into the ECU, infotainment system, and onboard diagnostics. The vehicle's VN is laser etched into the frame and stored electronically in Honda's global database. The car is now officially considered production complete. With the vehicle officially signed off from the production line, the next phase of the Honda Civic's journey is handled by a specialized logistics team responsible for organizing and staging vehicles for transport. At this point, every Civic has its final configuration, its color, trim level, engine variant, transmission type, and region-specific features all set in stone. But before it's shipped off to a dealership or distribution hub, it enters what's known as the Vehicle Outbound Logistics System. In a vast open-air vehicle yard adjacent to the assembly facility, often spanning hundreds of acres, you'll find hundreds, even thousands, of freshly minted Honda Civics parked in rows that stretch toward the horizon. This yard is not simply a parking lot, it's a tightly managed inventory control zone that functions like a living spreadsheet. Each Civic is tagged with an RFID chip or barcode label that links to a digital manifest. These digital profiles contain everything about the vehicle: where and when it was built, its VIN, trim level, market destination, port of discharge if being exported, and even its assigned dealership. Before entering this staging area, each vehicle is given a final scan at the gate. This scan confirms the completion of software installation, quality checks, and fluid top-offs. Once scanned, a logistics automation system assigns a parking spot based on the vehicle's outbound path. Cars, headed for rail transport, are parked near the loading tracks. Those bound for container shipping are staged by the dock ramps. Regionally distributed vehicles are positioned near road freight terminals. Each parking operation is choreographed with the help of a fleet of vehicle movers, some human, some automated. In newer facilities, autonomous electric tugs shuttle completed cars to their assigned staging rows, minimizing fuel usage and reducing human error. As the Civic arrives at its designated position, it is double-checked for cosmetic integrity. No scratches, no dents, and no contaminants like bird droppings or sap that could damage paint before delivery. Depending on the region, the vehicle may receive a light protective wrap, plastic sheeting on the hood, roof, and doors, as well as foam bumpers or wheel covers. These additions protect the finish during transport, particularly when Civics are being shipped across long distances via rail or ocean freight. From here, distribution diverges based on geography. Civics bound for nearby regions are typically loaded onto multi-level auto transport trucks, known as car haulers, using a hydraulic ramp system that maximizes vertical space. Each trailer can accommodate 8 to 10 vehicles, depending on size and configuration. Loading these haulers is a skillful job. Drivers must navigate tight clearances, especially when reversing a Civic up a narrow ramp just inches from another car's bumper. Once secured, the transport trucks depart along pre-planned routes, tracked in real time with GPS and monitored for weather, traffic, and delivery schedules. Vehicles typically arrive at regional distribution centers or directly at dealerships within 24 to 72 hours of departure, depending on distance. But for Civics headed overseas, the process is even more elaborate. Vehicles scheduled for export are transported to a port of exit, usually via rail. Special rail cars, called autoracks, are designed for this purpose. They're 3 levels high and feature secure wheel chocks, enclosed sides to protect from the elements, and locking mechanisms to prevent vehicle movement during transit. Before boarding the train, each Civic goes through a brief pre-rail inspection, checking tire pressure, door latches, and fuel levels. Vehicles must carry just enough fuel for loading and unloading, nothing more. Once the autoracks reach a port, often within a few days, the Civics are offloaded and prepped for ocean shipping. At the port, Honda works with marine logistics providers to board the vehicles onto roll-ons or roll-off vessels. These are essentially floating parking decks that can carry thousands of cars at once. A team of stevedores and vehicle handlers drives each car onto the ship via massive loading ramps. The cars are parked tightly together, locked down with wheel straps, and catalogued by location and destination. Each ship carries a mix of vehicles headed to different global markets, with each deck subdivided by destination. During the sea journey, which can last anywhere from 2 to 6 weeks, depending on the destination, the vehicles remain dormant but protected. Temperature, humidity, and salt exposure are controlled to prevent corrosion. Some ships use dehumidification systems to further protect sensitive electronics and cabin components. Upon arrival at the destination port, be it Vancouver, Rotterdam, Sydney, or Tokyo, the Civics are offloaded and moved to an inbound vehicle processing center. Here, local Honda representatives carry out market-specific inspections and final preparations. Depending on regulations and consumer preferences, some components may be installed at this stage. Market-specific infotainment systems, badges, labels, or compliance stickers. The battery is checked, tire pressure adjusted for the regional climate, and the vehicle is detailed one final time. Then, and only then, does the Civic make its final trip to a dealership, where it will be test-driven by prospective buyers and eventually become part of someone's daily life. The journey from raw steel coil to showroom floor is now complete. But behind this process is something even more impressive than the car itself: the manufacturing ecosystem that made it all possible. Every Honda plant, whether in Canada, Japan, the United States, or Thailand, is a model of lean manufacturing. Honda is one of the pioneers of flexible assembly, meaning the same line that produces the Civic may also produce other models with minimal downtime between them. This flexibility allows the plant to respond to shifting market demands without reconfiguring the entire factory. The chassis platform used by the Civic, for instance, might also underpin the Honda HR-V or Insight, all of which can be built on the same line with different modules and components swapped in real time. This orchestration relies on an advanced system of just-in-time supply chain logistics. Rather than stockpiling parts on-site, Honda's suppliers deliver components like dashboards, seats, HVAC modules, and wiring harnesses exactly when they're needed, often arriving at the plant just hours before installation. This minimizes inventory costs and allows for rapid changes to production volume or specification. Each component comes pre-labeled with a digital build sheet that identifies exactly which Civic it's meant for, ensuring flawless sequencing on the line. Complementing this is the just-in-sequence system, which goes one step further, delivering parts in the precise order of vehicle production. For example, if the assembly line is building a red Civic Sport, followed by a blue Civic X, the bumpers, headlights, and infotainment units for each car arrive in that exact order, pre-arranged for immediate installation. It's a ballet of logistics that requires real-time communication between Honda's central production servers and hundreds of Tier 1 and Tier 2 suppliers. To keep everything running smoothly, predictive maintenance is used throughout the plant. Equipment sensors track vibration, temperature, load, and wear in everything from conveyor belts to robotic welders. When a part shows signs of fatigue, the system schedules preventative maintenance before failure can occur, reducing downtime and improving safety. Quality control doesn't end once a vehicle leaves the line. Each factory maintains a dedicated audit station where randomly selected Civics are pulled for intensive testing. These vehicles are dissected and reviewed by expert inspectors who examine weld quality, paint thickness, body fitment, software behavior, and road performance. This data is fed back into the production process to flag trends or emerging issues, enabling Honda to respond proactively and maintain consistent quality. In terms of environmental responsibility, Honda's Civic production lines are engineered for energy efficiency and waste reduction. Water used in the paint booth is recycled through filtration and reverse osmosis systems. Paint overspray is captured by electrostatic filters and reused. Waste metal from the stamping plant is sorted robotically and returned to the steel mill for remanufacturing. Even the heat from curing ovens is repurposed to warm other parts of the facility. Power consumption across the plant is closely monitored and managed. Many Honda facilities are partially powered by solar arrays, wind energy, or cogeneration systems. Advanced lighting systems using motion sensors and LED technology ensure that energy is only used when and where it's needed. In some plants, Honda has achieved near-zero landfill status, meaning almost all waste materials, plastic, metal, rubber, even food waste, are recycled or repurposed in some way. Inside the modern Honda manufacturing plant, what might seem like a chaotic tangle of machines, parts, conveyors, and workers is in fact a precisely engineered environment orchestrated with clockwork efficiency. At this stage of production, where physical assembly transitions into post-production optimization and system refinement, the focus increasingly shifts from brute force manufacturing to intelligent systems management, what Honda refers to internally as manufacturing excellence. At the heart of this excellence is automation, an ever-present, evolving backbone of the modern Civic factory. Over 60% of tasks on the assembly line are now completed or assisted by robots. These are not simple, one-purpose mechanical arms, but intelligent, adaptable systems equipped with high-resolution sensors, 3D cameras, and real-time process feedback. In the body shop, robotic welders do far more than spot weld. They monitor the pressure of each weld in milliseconds, analyze the depth of each fusion, and dynamically adjust parameters to compensate for slight variations in steel thickness or surface contaminants. These adjustments happen in real time, with hundreds of data points captured per second and logged directly into Honda's centralized manufacturing database. Each of these robots is not just a tool, but a node in a larger intelligent network. That network, Honda's digital production control system, is built to track every Civic as it moves through the plant. From the moment a steel blank enters the stamping press to the final torque applied to the last wheel nut, the vehicle's identity is logged and linked to a database of component specifications, supplier batch numbers, sensor readings, machine parameters, and quality checks. This system allows Honda to maintain traceability, a key principle in modern automotive manufacturing. If a defect is ever found in a Civic's transmission casing or infotainment unit, engineers can instantly trace that part back to the day, time, and exact supplier lot it came from. This level of insight allows for surgical product recalls rather than sweeping generalizations, and is a cornerstone of Honda's commitment to quality and customer safety. In many zones of the factory, cobots or collaborative robots are replacing traditional industrial arms. These are smaller, more agile machines designed to work side by side with human operators. Unlike traditional robots that are fenced off behind safety barriers, cobots use proximity sensors, pressure feedback, and vision systems to detect the presence of humans and respond accordingly. For instance, in the trim assembly zone, cobots might assist a technician by precisely positioning heavy dashboard modules while the human secures them in place with fasteners. This reduces operator fatigue and improves assembly consistency, particularly for ergonomically challenging tasks that are difficult to automate entirely. Even AGVs, or automated guided vehicles, have seen substantial evolution. No longer confined to fixed track systems, newer Honda plants use vision-guided or LiDAR-based AGVs that navigate the factory floor independently, rerouting in real time to avoid traffic congestion or bottlenecks. These intelligent carts move everything from seats and dashboards to windshield glass and wiring harnesses, all without human input. Each AGV is linked wirelessly to the central factory control hub, which orchestrates their movements in relation to production flow. they are programmed to deliver specific components to a station at a precise time, synchronized with the exact Civic model being assembled at that moment. And this synchronization is not theoretical. Honda employs a modular assembly system, meaning that various trim levels, powertrain variants, and color options are built on the same line, back to back, without downtime. A Civic Sport with manual transmission might be followed directly by a Civic Touring with a CVT and an entirely different dashboard layout. Each workstation is equipped with smart tools, torque wrenches that automatically adjust to the specification required for that trim, vision systems that verify part fitment, and pick-to-light component bins that illuminate only the exact part required for that vehicle configuration. The system dynamically adapts the line to each unique build without requiring tool changes or reprogramming. In areas such as windshield installation or seat alignment, machine vision systems play a critical role. High-definition cameras capture detailed images of each step in the process, comparing live data to reference models stored in the system. These cameras can detect misalignments as small as 0.2 millimeters and instantly alert workers or trigger robotic correction. If a deviation is beyond correction thresholds, the system flags the vehicle and diverts it to a diagnostic bay for human evaluation. These inline quality checks are far more than visual. They're statistical safeguards, using large data samples to spot trends before they become problems. The paint shop, often one of the most energy-intensive parts of the plant, has also embraced advanced automation. Honda's robots not only apply base coats and clear coats with micron-level consistency, they also self-monitor the viscosity of paint, adjust spray patterns for optimal atomization, and even self-clean their nozzles between cycles. Overspray, which historically represented significant waste, is now captured by electrostatic plates and returned to a closed-loop reclaim system. Humidity and airflow in the paint booths are adjusted in real time to compensate for changes in ambient conditions, ensuring flawless finish consistency across seasons and global regions. Underpinning all of this automation is a layer of predictive analytics. Honda doesn't just react to faults, it forecasts them. Every sensor, robot, conveyor, and torque gun in the plant feeds data into a centralized AI-driven platform that looks for anomalies. If a certain fastener is being torqued more tightly than normal over a series of builds, the system flags the deviation. It may indicate tool wear, part misfit, or an upstream supplier issue. Engineers are alerted before a failure occurs. This predictive maintenance approach has dramatically reduced downtime and improved first-pass yield, an industry metric referring to the percentage of vehicles that pass inspection without needing rework. In the engine assembly hall, torque sensors are so precise they can detect if a technician has even one thread of a bolt cross-threaded. If detected, the system locks the build station, highlights the error on a display, and prevents the engine from moving forward until the issue is addressed. These safeguards ensure that even as production volume increases, Honda maintains the reliability and consistency that the Civic name is built upon. Lighting across the factory is controlled by intelligent energy management systems. LED lights adjust brightness based on time of day, production activity, and occupancy, cutting power usage dramatically. Heating and cooling systems adapt to the number of people in a zone and the thermal load of nearby machines. Even compressed air systems used in pneumatic tools and robotic actuators are monitored for leaks. Any pressure drop triggers an alert and isolates the zone for maintenance. These efficiencies not only reduce environmental impact, but also contribute to cost savings that allow Honda to reinvest in manufacturing innovation. As Civic production continues around the clock, every process, every station, and every worker is part of a living, learning system. The factory itself becomes smarter with time. Lessons learned from one batch of Civics are automatically integrated into subsequent runs. And when a mid-cycle refresh or new feature is introduced, say a redesigned infotainment interface or new powertrain calibration, the change is implemented digitally across the plant. Robots are updated wirelessly with new motion paths. Technicians receive augmented reality instructions via tablet. Parts suppliers are given revised sequencing instructions within minutes. As the Honda Civic continues its evolution on the global stage, one aspect of its production has grown increasingly central to the company's mission: sustainability. Manufacturing a modern automobile like the Civic requires immense amounts of energy, materials, water, and logistics, all of which must now be managed under the pressure of carbon emissions reduction and environmental stewardship. Honda's response to this challenge has been far from superficial. In many ways, its Civic production lines have become test beds for the company's broader efforts in building low-impact, resource-efficient factories. Every modern Civic plant is built with environmental performance targets baked into its architecture. From the outset, Honda employs what it calls Green Factory Principles, a framework of metrics and strategies for reducing energy consumption, carbon footprint, chemical emissions, and waste. These principles are applied at every level, from site selection to machinery operation. One of the most visible aspects of this sustainability initiative is Honda's aggressive use of renewable energy sources. Several Civic production plants, such as the one in Greensburg, Indiana, use large-scale solar panel arrays to offset electricity usage. These panels are often installed on the roofs of buildings or in dedicated solar fields adjacent to the facility. While they may not yet power the entire operation, they significantly reduce reliance on fossil fuels and provide a stable energy source for specific systems like lighting grids or HVAC. In addition, some facilities make use of combined heat and power systems, also known as cogeneration units, which burn natural gas to generate electricity on-site while capturing waste heat to provide hot water and climate control. These systems can be more than twice as efficient as pulling electricity from the grid alone, significantly cutting greenhouse gas emissions per kilowatt hour used. But it isn't just energy that's optimized. Water usage is a critical sustainability issue, particularly in the paint shop, where thousands of liters are required daily for rinsing, cleaning, and chemical mixing. Honda's solution has been the implementation of closed-loop water recycling systems. These systems use a mix of ultrafiltration membranes, reverse osmosis, and UV sterilization to clean and recirculate water through the plant. In some factories, as much as 95% of water used in production is reclaimed and reused. The E-Coat dip tanks, for example, are now topped off with recycled water that meets near laboratory-grade purity standards. Chemical usage in painting and metal treatment processes has also been re-engineered. Honda has transitioned many of its surface preparation and cleaning solutions to low VOC and phosphate-free alternatives. This not only reduces hazardous waste, but also improves worker safety and air quality inside the factory. Ventilation systems are fitted with electrostatic scrubbers and HEPA filters to capture overspray particles and solvent vapors, reducing emissions that would otherwise enter the atmosphere. Solid waste is handled with equal intensity. Modern Honda Civic plants operate on a near zero landfill policy. That means virtually all manufacturing waste, scrap metal, plastics, rejected parts, packaging materials, even cafeteria waste, is sorted, recycled, or repurposed. Steel offcuts from the stamping shop, for instance, are collected automatically by magnetic conveyors and baled for return to the steel mill. Plastic injection molding runners are ground up on site and reintegrated into new parts. Waste lubricants are filtered and reused for non-critical applications. To track the progress of these initiatives, every plant maintains a real-time environmental dashboard visible to both operators and management. This dashboard displays metrics like kilowatt hours per car produced, liters of water used per cycle, paint shop VOC emissions, and recycling rates. Engineers use this data to identify inefficiencies and launch Kaizen initiatives, small, continuous improvements that ripple across departments and compound over time. These dashboards are also shared across Honda's global factory network to spread best practices from one facility to another. That global network is itself a masterclass in distributed manufacturing. Unlike some automakers that rely on a single central plant for specific models, Honda's Civic production is distributed across multiple countries. This includes facilities in Japan, the United States, Canada, the United Kingdom, Thailand, and others depending on generation and market. Each of these plants is capable of localized production, a practice where the Civic is manufactured with regional suppliers, regulations, and consumer preferences in mind. For instance, Civics built for the North American market may feature different safety systems, infotainment options, or climate control calibrations than those produced for Southeast Asia or Europe. This localization reduces the carbon footprint of global shipping, lowers costs, and allows Honda to respond quickly to local demand. Supporting this decentralized system is a globally synchronized digital architecture. Through Honda's Global Production Operations System, every plant can access standardized blueprints, torque specs, quality benchmarks, and real-time engineering updates. If a supplier in Thailand discovers a defect trend in a batch of brake calipers, that information is immediately shared across the entire network, triggering preemptive inspections in other factories and supplier audits if necessary. It's a powerful example of how data is now just as important as steel in car manufacturing. These global factories are also adapting to accommodate a rising wave of powertrain diversification. As demand for cleaner transportation grows, Honda has committed to electrification, not just in full EVs, but also in hybrid and plug-in hybrid variants. For the Civic line, this means that certain factories now have dual powertrain capability, allowing them to produce both internal combustion and hybrid electric Civics on the same line. This feat of integration requires major adjustments to logistics, assembly sequencing, and training. Hybrid Civics require the installation of battery packs, inverters, high voltage wiring, and regenerative braking systems, all components absent in a traditional Civic. These parts arrive from Honda's dedicated eDrive suppliers, or in-house battery module assembly units. Once in the plant, they are carefully synchronized with the hybrid vehicle builds using the same just-in-sequence delivery system used for conventional components. Specialized battery handling equipment is required to safely transport and install the high-voltage packs, which are typically mounted beneath the rear seat or trunk floor. Technicians working in these zones receive additional safety training and wear insulated gloves, tools, and personal protective equipment. The factory floor is also reconfigured to include voltage-safe testing bays, where hybrid Civics undergo electrical system calibration, battery charge verification, and inverter diagnostics before leaving the plant. Furthermore, Honda is increasingly experimenting with modular EV production cells, small, independently operable lines dedicated to electric vehicle production. While not yet widespread for Civic manufacturing, these modular cells are being piloted as scalable units that can be added to existing facilities as EV demand grows. Their flexible footprint and self-contained operation allow them to be spun up quickly in response to market shifts. There's also a growing presence of simulation-driven design in the manufacturing pipeline. Before a new Civic variant ever hits the factory floor, it is built virtually inside a high-resolution, physics-accurate 3D model of the plant. Engineers can simulate every weld, fitment, fastener torque, and wiring route before any physical part is produced. These simulations help identify potential interference issues, ergonomic challenges, or inefficiencies long before they reach real workers or robots. The result is faster model ramp-up, fewer line stoppages, and improved first-time quality. Even the training of plant staff is evolving. New workers learn procedures not just from manuals or trainers, but through augmented reality overlays that guide them step by step. Wearing AR glasses or using tablets, they can see animated instructions projected onto real parts, highlighting the correct bolt, identifying the right clip location, or warning about torque sequence. This immersive training dramatically shortens the learning curve and reduces mistakes. Through all of these innovations, sustainable processes, global synchronization, powertrain diversification, and smart manufacturing technologies, the Honda Civic continues to set the standard for what a mass-market, high-efficiency automobile production line can achieve. And it does so not with gimmicks or short-term fixes, but with systems thinking, scientific rigor, and decades of accumulated expertise. The story of how a Nissan vehicle comes to life begins long before the first bolt is tightened or the first body panel is stamped. It begins in silence, inside vast facilities where architecture meets engineering precision, where design blueprints evolve into physical realities, and where automation and human craftsmanship converge in harmony. To understand how a Nissan car is assembled in a modern manufacturing plant, we must take a patient and measured walk through the process, beginning with the raw materials and the foundations of the factory environment itself. First, consider the raw ingredients. Unlike a loaf of bread or a bottle of juice, which may have fewer than a dozen components, a modern automobile contains tens of thousands of individual parts. These range from large body components to microscopic electronic sensors. Nissan vehicles are not built from a single supply chain, but from a sprawling network of global and regional suppliers. Raw steel, for example, is sourced from specialized mills that provide sheet steel of specific thickness, tensile strength, and corrosion resistance. These sheets often arrive in enormous coils, weighing several tons, each destined for a unique use, from structural frames to exterior body panels. But the metal itself isn't the only foundational ingredient. Aluminum is another critical player, especially in Nissan's push for lighter vehicles with improved fuel economy. Lightweight aluminum alloys are used in engine components, suspension arms, hoods, and doors. These materials arrive at the plant in various forms: flat sheets for stamping, extruded rods for machining, or even pre-formed castings for precision fitting. Plastics and polymers also play an indispensable role. Injection molded dashboards, center consoles, air ducts, bumper fascias, and even fuel tanks all depend on a continuous flow of petrochemical-derived resins. These arrive in pelletized form and are stored in high-capacity silos near the molding departments. Glass, rubber, wiring harnesses, textiles for seat upholstery, and electronics like sensors and infotainment systems all make up the broader raw material inventory. These are housed in precisely organized warehousing systems that operate using real-time inventory algorithms to maintain just-in-time delivery flows. Before any of these materials are touched, the factory environment itself must be primed. A Nissan plant is not just a series of conveyor belts and robotic arms. It is a living, breathing system engineered to the millimeter. The entire facility is divided into zones: stamping, body shop, paint shop, trim and chassis assembly, engine assembly, final testing, and outbound logistics. Each zone is temperature controlled, dust regulated, and equipped with fail-safe systems to ensure maximum uptime and worker safety. Let's begin with stamping, the first major transformation of raw material into recognizable vehicle form. The flat steel or aluminum coils are unspooled into long sheets, which are cut and fed into stamping presses. These aren't ordinary presses. They are massive hydraulic or servo-driven machines, each the size of a small house, capable of exerting thousands of tons of pressure in a single stroke. A typical press line consists of multiple stages. The first shapes the rough outline, the next adds structural reinforcement lines, and subsequent dies form the precise contours required for hoods, doors, fenders, and roofs. Each die set is a marvel of engineering, precision cut from tool steel, and maintained under strict tolerances. They are swapped out by automated systems depending on the vehicle model being produced. The forming process must be immaculate. Even a tiny wrinkle or deviation in the sheet metal can cause a cascade of issues downstream. For this reason, stamped panels are visually and dimensionally inspected using laser-guided scanning arms that map the surface of each piece in 3 dimensions, comparing it to digital blueprints accurate down to fractions of a millimeter. Once the panels pass inspection, they are automatically stacked and routed to the next zone, the body shop. This area represents one of the most robotics-intensive sections of the plant. Here, high-precision robotic arms work in orchestrated sequences to weld the stamped components together, forming the skeletal structure of the car, also known as the body in white. This name refers to the unpainted raw metal form of the vehicle before it is sent to the paint shop. To build a car's body with millimeter accuracy, Nissan uses jigs and fixtures that align each piece into place before welding. The majority of the welding is done via resistant spot welding, in which 2 electrodes press against a metal panel and send a high current, low voltage electrical pulse through it, melting the metal at the contact point to form a durable weld. A typical car body will undergo thousands of such welds, and each weld point is tracked in a centralized database, ensuring quality consistency across every unit. However, not all joints are welded. In strategic areas where welding might introduce too much heat or stress, such as near-thin aluminum panels or multi-material junctions, Nissan uses structural adhesives and flow drill screws. Structural adhesives bond dissimilar materials together with incredible strength, while flow drill screws are self-tapping fasteners that create their own hole during insertion, eliminating the need for pre-drilled pilot holes. These innovations not only reduce weight, but also improve crashworthiness and reduce manufacturing cycle time. Robotic vision systems equipped with infrared and laser sensors ensure that each weld, screw, and bond is placed with pinpoint accuracy. Human technicians oversee the process, intervening only when a discrepancy or anomaly is flagged by the system. This collaboration between machine and operator defines Nissan's approach to manufacturing. Automation, where it boosts consistency and speed. Human touch, where judgment and adaptability are required. At this stage, the vehicle body still lacks color and character. It resembles a raw metal shell, cold, industrial, and devoid of personality. That all changes when the body in white moves to the paint shop, which is perhaps the most climate-controlled and sterile part of the plant. Before the vehicle even sees a drop of paint, it must undergo surface preparation, which begins with a multi-stage chemical bath known as the pre-treatment process. The body is first submerged in large vats of alkaline cleaner to strip away oils, residues, and metallic debris from previous operations. Following this, the body enters successive baths of rinse water, deionized water, and eventually a phosphate solution that chemically etches the surface. This phosphate layer provides corrosion resistance and improves paint adhesion. All of this is conducted using massive hoists and carrier systems that dunk and rotate the body at precise angles to ensure total coverage inside and out, including hidden cavities and internal seams. Next, the body is moved to the electrode deposition tank, or e-coat bath. Here, the entire shell is submerged in an electrically charged solution containing water-based epoxy. By applying a positive electrical charge to the vehicle and a negative charge to the tank, the paint particles are attracted and bonded uniformly to the metal surface. The result is a perfectly even, rust-resistant primer layer that coats every inch of exposed and hidden metal, forming the foundation for the subsequent layers of base coat and clear coat. This e-coated shell is then baked in a high-temperature oven to cure the primer. The body is carefully cooled afterward, and only then is it ready to receive its final paint layers, which we'll delve into in greater detail in the next segment. After the e-coated body is fully cured and cooled, the shell is directed into one of the most visually impressive parts of the manufacturing process, the paint shop. This area is entirely climate controlled, with tightly regulated humidity, temperature, and air purity. Any dust, hair, or particulate matter introduced at this stage could compromise the flawless finish expected of a Nissan vehicle. For this reason, all air entering the paint shop passes through high-efficiency particulate air filtration systems, and many areas operate under positive pressure to push contaminants away from the vehicle surfaces. The first phase in this stage is the application of the base coat, which gives the vehicle its recognizable color. Robotic paint arms mounted on programmable tracks glide gracefully along the length and height of the car, applying atomized paint in multiple passes. These robots are equipped with electrostatic sprayers, which charge the paint particles to ensure they adhere evenly and efficiently to the grounded car body. This process not only ensures a uniform coating, but also reduces overspray and environmental waste. Each model has its own programmed paint trajectory, accounting for variations in body shape and surface geometry. High traffic areas, like bumpers and door edges, may receive additional coats for added durability. Nissan uses waterborne paints to minimize volatile organic compound emissions, a key part of their environmental stewardship commitments. After the base coat is applied, the vehicle enters a controlled flash-off zone where the solvents are allowed to evaporate under gentle heat and airflow before the next layer is applied. Once the base coat is dried, the vehicle proceeds to receive its clear coat layer. The clear coat is a transparent, high-gloss, protective layer that not only enhances the visual depth of the color, but also shields the paint from ultraviolet radiation, road debris, and environmental contaminants. Like the base coat, it is applied robotically with fine control, and afterward, the vehicle passes through a large baking oven where the clear coat is cured at high temperatures for a precise amount of time. When the vehicle emerges from the curing oven, it gleams with a showroom quality finish. But this stage is not the end of the paint journey. Human inspectors take over here. Under intense overhead lighting, trained technicians visually and tactilely inspect each surface, feeling for imperfections and searching for inconsistencies. Small flaws, like dust nibs or uneven orange peel texture, are meticulously polished out using ultra-fine sandpaper and buffing tools. This hands-on quality check ensures every painted body meets Nissan's cosmetic and durability standards. Now painted and gleaming, the body is transferred to a storage buffer zone while it awaits further assembly. These buffer systems are often automated, with conveyors and elevators storing completed bodies in multi-level racks, sorted by production sequence to ensure that the correct vehicle body matches the correct chassis and engine components downstream. Meanwhile, deep inside another part of the plant, an equally sophisticated and critical process is unfolding: the engine assembly. Nissan builds many of its engines in-house, often in the same complex as the final vehicle assembly line. These engine shops operate with surgical precision, combining cleanroom practices with high throughput automation. Engine production begins with core components: the cylinder block, crankshaft, cylinder head, camshafts, pistons, and connecting rods. The raw castings for these components are typically received from external foundries and then machined in-house. Large CNC machining centers mill the cylinder bores, bearing journals, oil galleries, and mounting faces with micron-level precision. Robots move castings between operations, and automated coordinate measuring machines verify dimensions at each stage. Each cylinder block is washed and deburred, then moved to the sub-assembly line. The crankshaft is inserted into the lower block and supported by main bearings, with torque-controlled machines tightening bearing caps to exact specifications. Pistons and connecting rods are assembled and inserted into the bores, connected to the crankshaft via piston pins, and rotated through their full stroke to verify smooth movement. The cylinder head, which contains the intake and exhaust valves, valve springs, and camshaft journals, is assembled next. Once the valve train is complete, the head is placed on top of the block and fastened with head bolts torqued in a precise sequence. Camshafts and timing components are installed, and the engine is rotated again to ensure timing alignment. What makes Nissan's engine assembly lines unique is their level of integration between automation and manual craftsmanship. While many of the tasks, like bolt tightening, parts insertion, and lubrication, are done by robotic arms or torco wrenches mounted on manipulators, human technicians are constantly monitoring alignment, oil sealing surfaces, and small tolerance adjustments. Certain high-performance or hybrid powertrains even require hand assembly by specially trained master technicians. Each completed engine undergoes a series of tests before moving forward. Cold testing stations spin the engine using external electric motors to verify internal friction, pressure buildup, and sensor communication, all without firing a single drop of fuel. Any deviation from the norm triggers a quality control flag, removing the unit for further inspection. Parallel to the engine line, transmissions are assembled using similar methodologies. Whether it's a continuously variable transmission, a manual gearbox, or a dual clutch system, each transmission unit undergoes assembly with exacting precision. Gear stacks, clutch packs, torque converters, and electronics are pieced together in sequences governed by computer-guided workstations. Like engines, each transmission is cold tested and electronically validated before release. As the engines and transmissions reach completion, they converge on the powertrain marriage station, a section of the plant where the powertrain is physically combined with the vehicle chassis and body. But before we reach that critical moment, we must pass through the trim and chassis assembly line, where the empty painted shell slowly transforms into a functional car filled with thousands of components. Before any parts are added, the painted body shell is prepped by attaching sound deadening pads and insulation materials. These are critical for reducing noise, vibration, and harshness, often referred to as NVH characteristics, and are strategically placed on the floor, inside door cavities, and along the firewall between the engine bay and cabin. Next, the vehicle enters the trim line. Here, the interior comes to life. Wiring harnesses are the first components installed, snaking through every crevice and corner of the vehicle. These harnesses are complex bundles of electrical wires, connectors, and terminals, enabling everything from headlight operation to GPS functionality. Depending on the model, there may be miles of wire bundled into various looms. Installers use routing guides and retention clips to fasten these bundles into the frame with impeccable consistency. Once wiring is in place, the dashboard, HVAC system, pedals, steering column, and electronic control modules are installed. These components arrive pre-assembled in modules to improve efficiency and accuracy. Operators use mechanical lifts and alignment jigs to position the large dashboard unit into the front of the cabin. Screws are torqued automatically, and alignment pins ensure everything fits perfectly. Seats, carpets, door panels, airbags, and interior trim components are installed in a choreographed sequence. Workers use rolling stools and robotic assist arms to move around the vehicle efficiently, guided by digital work instructions displayed at each station. Cameras and sensors verify part presence and correct orientation. Each vehicle configuration whether leather or cloth, manual or electric seats, right or left-hand drive, is tracked digitally and updated in real time to prevent errors. While this is happening, another line is assembling the vehicle's chassis modules. This includes suspension assemblies, brake lines, steering gear, fuel tanks, and axles. These are pre-built into front and rear subframes that can be quickly bolted to the vehicle in a marriage station. The subframes are transported via automated guided vehicles that navigate the plant floor using magnetic strips or laser-guided navigation. The marriage station is more than just a mechanical juncture. It's a moment of transformation. Up until this point, the vehicle has existed as a painted shell, fully trimmed on the inside, but motionless and lifeless. Meanwhile, the engine, transmission, and chassis have been independently assembled, inspected, and prepared. Now, all these major systems converge in a single, highly orchestrated step that literally brings the vehicle to life. The process begins with the body shell being lowered from an overhead conveyor or scissor lift system onto the rolling chassis unit, which includes the engine, transmission, front and rear suspension, axles, and exhaust system. To align both structures perfectly, alignment pins, sensors, and robotic positioning systems are used. These ensure that mounting points for the subframes, powertrain supports, and drive shafts line up with millimeter-level accuracy. Torque-controlled robotic arms then secure bolts through carefully designed mounting points to bond the body and chassis into a single, integrated structure. Once the powertrain is secured, technicians connect vital systems that bring the car's components into communication with each other. Fuel lines are attached from the tank to the engine. The exhaust manifold is mated to the underbody exhaust system. Brake lines are connected to the master cylinder and calipers, and the steering column is physically linked to the rack and pinion assembly. Electrical connectors from the wiring harness are snapped into their respective control modules on the engine and transmission. These quick connect systems are designed for both speed and reliability, allowing each connection to be completed in seconds, but still capable of enduring thousands of hours of vibration, moisture, and thermal cycling. With the vehicle now resting on its permanent chassis, the next step involves installing the wheels and tires. These assemblies are often pre-mounted and balanced at a separate tire center. Wheels are aligned on automated carriers and positioned next to each vehicle on the line. A robotic wheel installer or pneumatic torque wrench system fastens each lug nut in a star pattern, applying precisely calculated torque values to ensure even stress distribution across the wheel hub. This level of precision is essential not just for safety, but also to avoid issues such as uneven brake wear or tire vibration later on. With wheels in place, the vehicle is now fully grounded. It rolls off the marriage platform and moves on its own wheels for the first time. This moment is symbolically significant. It's the first time the vehicle exhibits mobility, but it's still not ready to run. Several fluid systems must now be filled and primed. The fluid fill area is a long stretch of the assembly line where dedicated stations automatically or semi-automatically fill the car with all necessary operating fluids. This includes engine oil, coolant, transmission fluid, brake fluid, power steering fluid if applicable, and windshield washer solvent. Each fluid has its own robotic fill nozzle mounted on articulated arms that connect to service ports with leak-free seals. The systems behind these nozzles monitor flow rates, fluid volumes, and pressure levels during the fill process. If a sensor detects a slow fill rate, potential air bubble, or leak, the system will automatically flag the vehicle for inspection. Coolant systems are pressurized and tested for leaks. Brake lines are vacuum bled to remove air and ensure proper hydraulic function. This is a critical stage where even a minor error could result in a major safety issue down the line, so every fill operation is closely monitored and logged in the vehicle's digital production record. After fluids are filled, the vehicle moves into the electrical initialization zone. Here, battery packs are installed, either traditional 12-volt batteries or high-voltage systems for hybrid or electric models. Once power is connected, the Central Electronic Control Unit, or ECU, is activated for the first time. This moment is often referred to as the initial software boot. It's the digital awakening of the vehicle when thousands of control modules across the car begin talking to each other for the first time. Diagnostic tools connect to the onboard diagnostic port and run a full check of the vehicle's electrical and software systems. Every sensor, actuator, light, motor, and module is tested for proper operation. Software is flashed or updated as needed, depending on the production sequence and region of delivery. The vehicle is now a networked system, with the ECU serving as the brain, overseeing everything from throttle control to driver assistance systems. Once the electronics are live and fluid systems primed, the engine is ready for its first start. This first ignition is more than symbolic. It's a functional validation. At a designated startup station, technicians press the ignition button or turn the key for the first time. The engine roars to life, monitored by sensors that check for oil pressure, fuel system integrity, idle speed, and exhaust emissions. On hybrid or electric models, this step includes motor calibration and verification of battery charge levels. After the vehicle starts successfully, it proceeds to the alignment and calibration zones. Here, specialized machines verify that the wheels are aligned to factory specifications. Cameras and laser-based alignment systems measure camber, toe, and caster angles in real time. If any value is out of tolerance, the system automatically adjusts suspension linkages or control arms using powered adjustment tools. At this stage, cameras, radar sensors, and LiDAR modules are also aligned. These advanced driver assistance system components must be perfectly calibrated to ensure accurate lane keeping, adaptive cruise control, and emergency braking functions. Large panels with printed targets are positioned around the vehicle, and specialized cameras mounted on robotic arms adjust sensor aim and focus using software-controlled procedures. Once alignment is verified, the vehicle enters the dynamic test track area within the factory. This is an indoor or covered track designed to simulate real driving conditions at low speeds. The car is driven over bumps, through slalom curves, and across vibration plates. Brakes are applied at various intensities. Steering feedback is tested, and transmission shifts are observed. For EVs, motor torque and regenerative braking performance are measured. Trained drivers listen for abnormal sounds, vibrations, or behaviors. Any deviation from expected performance sends the vehicle to a diagnosis bay for further investigation. Vehicles that pass this functional road test move forward to water leak testing. They enter a sealed booth where a controlled shower simulates a heavy downpour. Water jets spray the vehicle from every direction for several minutes while technicians observe from inside the cabin. Any sign of water intrusion leads to immediate inspection and resealing. At this point, the vehicle is mechanically and electronically complete. What remains is finishing, final trim pieces, protective coatings, detailing, and inspections. Workers install badges, model emblems, VIN plates, tire pressure stickers, and other regulatory labels. Plastic protective films are applied to touch surfaces, such as door sills and infotainment screens, to prevent scuffing during transport. Some factories even spray a fine protective wax on the underbody and exposed metal areas for added corrosion resistance during shipment. A final quality audit takes place before the vehicle is cleared for shipment. This audit involves a checklist that covers over 300 inspection points: paint quality, panel gaps, door alignment, trunk closure force, hood latch function, seatbelt retraction speed, HVAC operation, infotainment interface responsiveness, and much more. Every light, switch, lever, and button is activated. Even the smell of the cabin is considered. It must match Nissan's strict standards for interior air quality and finish. Vehicles that pass this rigorous final inspection are driven a short distance to the shipping yard, where they are staged based on destination and production date. From here, they will be loaded onto multi-car transport trucks, rail cars, or roll-on/roll-off cargo ships, depending on their final market. While the sleek vehicles rolling off the final inspection line might seem like the pinnacle of the process, the truth is that the visible assembly is just the surface of a far more intricate system humming in the background. Beneath the polished robotics and synchronized welds lies the real engine of Nissan's manufacturing philosophy, its logistics and supply chain network. Every bolt, bracket, circuit board, and carpet panel that enters the Nissan production line must arrive at exactly the right time, in the right quantity, and at the right location. Any deviation, even a late shipment of a single component, can grind an entire production line to a halt. That's why Nissan operates on the principles of just-in-time and just-in-sequence production. Just-in-time, or JIT, means that components are delivered to the factory floor precisely when they're needed, not days or weeks in advance. This minimizes on-site inventory, reduces storage costs, and prevents parts from becoming obsolete or damaged. The process starts with Nissan suppliers, many of which operate their own mini factories or warehouses within a short radius of the main plant. These are known as supplier parks or vendor villages, and they play a crucial role in facilitating rapid part delivery. Within these supplier parks, Tier 1 vendors receive real-time signals from the Nissan plant via an integrated data exchange system. As a vehicle moves down the line and specific parts are consumed, such as a steering wheel or instrument cluster, the inventory software triggers an automatic order for replenishment. This order is sent instantly to the supplier's production line or warehouse, prompting them to pack and ship only the exact number of units needed. The goal is zero excess inventory. Materials often arrive in reusable shipping containers, pre-sorted for each specific car build, which are then returned for reuse. But JIT alone isn't enough for modern car manufacturing. Nissan also uses just-in-sequence or JIS logistics to match parts not only to the time of arrival, but to the exact vehicle configuration. Consider two vehicles moving down the line back to back. One may be a red crossover with black leather seats and a premium audio system, while the next could be a white base model with cloth interior and fewer features. The parts arriving at each station must match these exact builds. To achieve this, every car on the line is tracked by a vehicle identification number or VIN and a build manifest stored in the central production system. As the car enters each work cell, scanners and RFID tags identify it, prompting the delivery of precisely the right parts for that configuration. Automated guided vehicles, or AGVs, often carry these parts from the warehouse to the line, moving along predetermined tracks, or using laser navigation systems to avoid collisions and delays. These AGVs are programmable, flexible, and highly reliable. Some Nissan plants have hundreds of them in constant motion, shuttling dashboards, doors, engine modules, seats, and even air conditioning units. Each AGV is linked to the factory's Manufacturing Execution System, or MES, which manages scheduling, tracks the position of each vehicle in real time, and issues movement commands based on production needs. To make sure the right parts are always on hand, Nissan employs Kanban systems, visual signals, often in the form of barcodes or RFID tags, that are attached to each part's bin. When a bin is emptied at the line, the Kanban signal is scanned and sent to the warehouse, triggering a restock. In some plants, drones or robotic arms handle the physical movement of bins in the parts warehouse, pulling from high-density racking systems where parts are stored based on velocity and frequency of use. At the heart of all this is data. Nissan's factories are built around Industry 4.0 principles, meaning they are digitally interconnected, sensor-driven, and algorithmically optimized. Every robotic weld, torque wrench operation, fluid fill, and software update is logged in real time into a central cloud-based system. This system not only stores quality assurance data, but also enables predictive maintenance. If a welding robot begins operating at slightly higher amperage than normal, or if a torque wrench shows signs of calibration drift, the system can predict failure before it happens and alert technicians to intervene. This proactive approach avoids costly downtime and ensures that every vehicle produced meets consistent quality standards. The data also flows upward to regional headquarters and global management teams, allowing executives to monitor production volumes, part consumption rates, and labor efficiency from anywhere in the world. In terms of factory layout, Nissan designs its plants using modular zones, where each zone focuses on a specific function but remains physically and digitally linked to adjacent ones. These zones are often arranged in a U-shaped or serpentine flow, allowing for compact, efficient use of space and easy transfer of vehicles from one stage to another. Overhead monorails, automated elevators, and conveyor belts link the zones, while overhead digital screens and projection systems guide workers on each task to be performed for each car. Automation plays a dominant role but is not total. Human workers are still critical for tasks that require dexterity, tactile feedback, or judgment, such as installing fragile interior trim, adjusting panel gaps by hand, or performing final visual inspections. Nissan emphasizes human-machine collaboration, training its workers not only to install parts, but to manage robotic systems, interpret diagnostic data, and lead continuous improvement initiatives. To empower its workforce, Nissan has established Kaizen programs in every plant, small, team-led groups that regularly review their own work processes and propose enhancements. These improvements could involve ergonomic tool redesigns, reorganization of workstation layouts, or software refinements in part scanning systems. Suggestions are submitted daily, reviewed weekly, and implemented rapidly when proven effective. This bottom-up approach to optimization not only improves efficiency, but fosters a culture of ownership among workers. Alongside efficiency, sustainability is also a growing focus. Nissan's plants are increasingly powered by renewable energy sources, including solar panels, wind turbines, and energy recovery systems that capture waste heat from ovens or motors. Many facilities employ closed-loop water systems for cooling and paint booth operation, significantly reducing freshwater consumption. Waste materials like scrap metal, used oils, and excess plastics are sorted and recycled through dedicated processing centers on-site or nearby. Even the vehicle's logistics post-production are managed with environmental and efficiency goals in mind. Once a car is approved and staged in the shipping yard, a transportation management system determines the optimal delivery method based on destination, vehicle type, and urgency. Railcars are loaded using automated platforms, and cargo ships, often managed by Nissan's own fleet division, use roll-on/roll-off ramps to drive vehicles directly aboard with minimal manual handling. To minimize carbon emissions, vehicle loads are planned to eliminate empty return trips, and shipment routes are optimized to reduce travel distance and idling. In some markets, regional distribution centers are outfitted with charging infrastructure, allowing electric vehicles to be shipped at lower charge levels and topped off closer to the final dealership, reducing battery degradation during transport. So while the final vehicle may be the most tangible result of the process, the true marvel lies in the orchestration behind it. The invisible threads of data, logistics, robotics, and human expertise that keep each Nissan plant operating like a symphony. Every second, every motion, every part is tracked, timed, and optimized. With the vehicle fully assembled, tested, inspected, and polished, it is driven out of the factory's final inspection bay and onto a staging lot, a large, open-air shipping yard arranged with geometric precision. Here, vehicles are grouped based on model, trim level, destination region, and transport mode. While the car is now complete from a manufacturing perspective, the post-production logistics chain has only just begun. At this point, each vehicle carries a barcode or RFID tag that identifies every step of its production history, component list, software version, and destination. This digital tag continues to be scanned at each stage of post-factory handling, creating a living data trail that accompanies the car until it reaches the dealership, and sometimes beyond. From the staging lot, most vehicles are loaded onto specially designed transporters. These can be multi-deck car carrier trucks, capable of hauling up to 10 vehicles at once, or in high-volume markets, they may be driven directly onto rail cars. In coastal or international markets, vehicles are loaded onto roll-on/roll-off cargo ships, which are essentially floating multi-level garages where vehicles are driven aboard by professional operators and parked in precisely assigned locations. These transport decisions are based on an algorithmic system that weighs time to delivery, vehicle demand forecasts, fuel efficiency of transport mode, and cost. For example, a vehicle destined for a high turnover dealership in a major metro area might be prioritized for truck transport to shave days off delivery time. Meanwhile, vehicles going to remote or rural areas may be consolidated into rail or sea shipments for efficiency. As the vehicles leave the factory premises, they remain under Nissan's logistical control via a global transportation management system. This platform allows central and regional teams to track every shipment in real time, identifying bottlenecks, delays, or weather-related issues that might impact delivery. The system also manages estimated time of arrival, updating dealerships with live delivery windows so they can prepare for intake, inspection, and customer scheduling. Once the vehicle arrives at a regional distribution center, or RDC, it undergoes what is known as dealer preparation or pre-delivery inspection. These centers act as the bridge between the factory and the dealership showroom. The goal here is to ensure that every vehicle arrives in pristine condition and is fully ready for customer handover. The first step in dealer prep is a transportation damage inspection. Technicians walk around the vehicle with inspection checklists and tablet-based software, documenting any scratches, dings, fluid leaks, or scuff marks that may have occurred during transit. Although the entire logistics chain is designed to minimize movement and reduce risk, minor damage is still possible during loading and unloading. In such cases, paintless dent repair, polishing, or even panel replacement may occur before the vehicle continues downstream. Next, the vehicle enters a detailing bay where it is washed, cleaned, and visually enhanced for showroom readiness. Protective shipping films, the white plastics that cover door edges, hood panels, or infotainment screens, are removed, and the vehicle's interior is vacuumed, glass polished, and tires shined. In cold climates or during seasonal transitions, winter or all-season tires may be mounted if requested by the dealer or customer. Following cosmetic detailing, technicians perform a functional validation. This includes starting the engine, checking dashboard lights, updating software to the latest available version, confirming proper tire pressure, topping off fluids if necessary, testing the infotainment system, verifying remote key fob operation, and ensuring all driver assistance features like lane departure warnings, adaptive cruise control, or rear-view cameras are fully operational. Once complete, the vehicle is assigned to a dealer stock list and released for final delivery. In many cases, dealership staff will come to pick up the vehicle directly from the RDC. In others, it will be trucked the final leg of the journey, often no more than a few hundred kilometers, to arrive on the dealer's lot. Even this final trip is tracked and timed. When the car arrives at the dealership, it enters a final phase of human interaction. Sales and delivery staff may apply dealership branding, affix local license plate brackets, or even install optional accessories that were requested at the point of sale. Some dealers offer ceramic coatings, floor mat upgrades, custom badging, or window tinting. Value-added services that help personalize the vehicle for its future owner. Now, for the first time, the vehicle's story intersects with the customer. Whether purchased in person or ordered online through Nissan's digital retailing platform, the buyer is informed that their vehicle is ready. Many buyers never realize how recent the final factory steps were. In many cases, less than 10 days separate the moment the last bolt was torqued in the factory from the moment they received the keys. Before handing over the vehicle, most dealerships will perform a customer delivery walkthrough. This involves demonstrating how to use all key systems, pairing a phone with Bluetooth, adjusting seat memory positions, configuring driver profiles, navigating the touchscreen interface, and explaining the vehicle's service schedule. For electrified vehicles, staff walk customers through charging protocols, estimated range behavior, regenerative braking modes, and home charger options. But Nissan's involvement doesn't end once the keys are handed over. Every vehicle sold is still tethered to the manufacturer's digital service infrastructure, which includes remote diagnostics, over-the-air updates, warranty tracking, and predictive maintenance alerts. Modern Nissans, especially those with Nissan Connect, are equipped with telematics units that can transmit vehicle health reports, detect trouble codes, and even recommend service appointments. Through this connected system, Nissan can monitor the performance of entire vehicle fleets, identify recurring service issues, and even preemptively recall batches of vehicles if a defect is detected statistically. Dealerships receive diagnostic data in advance, meaning that when a customer drives in for service, the technician already knows what to expect and what parts may be needed. Additionally, every service performed at an authorized dealer is uploaded to a vehicle service history database, providing transparency for both the manufacturer and future resale. This connection between factory, dealer, and customer creates a full lifecycle data loop that supports ongoing quality improvements and customer satisfaction. Behind the scenes, Nissan also uses customer feedback and market analytics to inform future production. Purchase patterns, option uptake, color popularity, and return maintenance data all feedback into the company's planning divisions. This helps refine inventory decisions, forecast parts demand, and even shape the designs of future models. For example, if a particular trim package is consistently chosen in combination with a certain wheel option or driver assistance suite, that configuration may be bundled into a new trim level to streamline ordering and improve plant efficiency. Likewise, if a specific infotainment issue is repeatedly flagged in customer feedback, Nissan's engineering and software teams are notified and tasked with investigating. In this way, every Nissan vehicle is not just the product of a one-time manufacturing event, but the node in an ongoing relationship between machine, human, data, and organization. Each car that leaves the factory becomes an extension of Nissan's global strategy, a testbed for improvement, a data source for refinement, and a living example of manufacturing precision. The customer may never see the Weld robots, the e-coat tanks, or the AGVs that moved their dashboard into place. But within the tactile feel of the gear shift, the gentle click of a climate control button, or the quiet hum of the motor lies the fingerprint of an entire industrial ecosystem. The Nissan vehicle is the visible result of millions of invisible decisions, flawlessly synchronized in time and space. The journey starts in Chevrolet's design and engineering departments, where teams of designers, mechanical engineers, and manufacturing planners work together to create not just the look of a vehicle, but the exact way it will be built. The earlier stages are dominated by design feasibility. Engineers ensure that the proposed vehicle shapes, curves, and mechanical layouts are compatible with large-scale manufacturing techniques. This includes determining how each body panel will be stamped, how wiring harnesses will be routed, and how components will be positioned for both performance and serviceability. It is here that design for assembly comes into play. In every element must be optimized for efficient installation without compromising quality or safety. This is especially critical for Chevrolet, which produces a wide range of models, from compact sedans to full-size trucks, each with very different manufacturing needs. Once the design is finalized, manufacturing engineering takes the blueprint and transforms it into a step-by-step factory plan. This involves defining which machines, robots, and tooling will be used at each stage of production, how workers will interact with them, and how the line will be sequenced to handle multiple model variations. Many Chevrolet plants are designed for mixed model production, meaning that a pickup truck and a crossover SUV could be assembled back-to-back on the same line. This requires extremely precise scheduling and tooling flexibility. The process begins with raw material arrival, particularly steel and aluminum sheets that form the vehicle's structural backbone. These materials arrive at the stamping plant in the form of enormous coils, each weighing many tons. The coils are unrolled, cut into blanks, and fed into massive stamping presses. These presses, some of the largest machines in the automotive world, shape the metal into fenders, roofs, doors, and other body panels using dies that weigh several tons themselves. Each panel typically goes through several stamping stages, moving from a rough shape to precise final contours. During stamping, dimensional accuracy is paramount. Even a fraction of a millimeter of error can cause alignment issues later in the build. Chevrolet uses automated inspection systems to verify each panel's geometry, rejecting or recycling any piece that fails to meet exact standards. This quality control in the stamping phase prevents costly rework later down the line. From stamping, the panels move into the body shop. Here, the flat, separate pieces are joined together to form the body in white, the term for the bare, unpainted vehicle shell. This process is dominated by robotic spot welding, where arms with welding guns move in perfectly choreographed sequences to fuse the panels together. The body shop operates on a combination of fixtures and jigs that hold each piece in precise alignment, ensuring structural strength and proper fit. The floor pan is laid down first, then side panels, roof structures, and reinforcements are added in a sequence determined by both structural integrity and manufacturing efficiency. Chevrolet plants use hundreds of welding robots, but human oversight remains critical. Skilled technicians monitor the welding cells, handle complex welds in tight spaces, and conduct random sample checks to confirm that weld penetration and positioning meet specifications. In some areas, adhesive bonding is used alongside welding to increase rigidity and reduce noise, vibration, and harshness. After the body is fully assembled, it undergoes detailed dimensional checks using coordinate measuring machines or laser scanning systems. If all is within tolerance, the body in white moves to the paint shop. The paint process is one of the most controlled environments in the factory, as even a speck of dust can mar the finish. The first step in painting is cleaning and pre-treatment. The body is submerged in a series of chemical baths to remove grease, oils, and contaminants. A phosphate coating is then applied to improve corrosion resistance. This is followed by the electrophoretic deposition, or E-coat, where the body is dipped in a charged primer bath that ensures complete coverage in every nook and cavity. The E-coat is then baked to cure it into a durable base layer. Once primed, The body passes through sanding and inspection areas before moving to the color base coat booths. Chevrolet's paint lines often use robotic spray arms programmed to follow complex paths that ensure an even application over curves, edges, and recessed areas. Some vehicles receive two-tone paint or special finishes, requiring masking and multiple spray cycles. The base coat is followed by a clear coat, which provides gloss and protection from UV rays and environmental wear. Each coat is baked in ovens to cure it, hardening the finish for durability. After the final paint cure, the body emerges looking complete on the outside, but it is still just a shell with no functional systems. This is where the trim and chassis assembly phases begin. The painted bodies move onto the trim line, where workers and robots install interior components in a carefully sequenced order. Wiring harnesses are routed through the body, HVAC ducting is fitted, and dashboards are installed as complete units. Seats, carpets, door panels, and center consoles are added, with quality checks at each station. Parallel to this, in another part of the plant, chassis sub-assemblies are being prepared. Engines, transmissions, front and rear suspension units, exhaust systems, and brake assemblies are mounted onto subframes. This pre-assembly ensures that when the time comes, the drivetrain can be installed into the body quickly and accurately. With the major mechanical and trim installations complete, the Chevrolet moves into the final assembly verification and testing phase. At this point, the vehicle is fully recognizable, but its systems have yet to prove themselves under controlled evaluation. This stage is where the factory shifts its focus from building to validating. One of the first stops is the wheel alignment station. Using laser-based or camera-guided systems, technicians check the alignment angles for each wheel: camber, caster, and toe. Proper alignment is essential not only for safe handling, but also for tire longevity and fuel efficiency. Adjustments are made at the suspension components until all readings are within Chevrolet's specified tolerances. These specifications are tied to each model's unique suspension geometry, ensuring consistent road feel across every unit. Next, the vehicle proceeds to the fluid fill and system pressurization stage. While many fluids, such as engine oil, brake fluid, and coolant have been partially filled earlier in the assembly process, this step ensures that all are topped off to exact levels and that the systems are free of leaks or trapped air. For braking systems, pressure testing and bleeding are performed to guarantee firm pedal feel and consistent stopping power. The fuel system is also pressurized and checked for leaks, as even minor seepage can create both safety and emissions compliance issues. Then comes one of the most exciting moments on the factory floor: the first engine start. At a dedicated startup station, the technician engages the ignition, bringing the Chevrolet's powertrain to life for the very first time. The engine's idle is monitored closely for smoothness, proper fuel-air mixture, and the absence of unusual noises or vibrations. The onboard diagnostic system is immediately scanned to ensure no fault codes are present. If a code does appear, it is addressed on the spot before the car moves on. After the initial start, the vehicle advances to the rolling road test, also known as the dynamometer station. Here, the car's drive wheels rest on large rollers that simulate real road resistance. A trained operator runs the vehicle through different speed ranges, gear changes, and acceleration profiles, while onboard sensors monitor performance. For automatic transmissions, shift smoothness is evaluated. For manual transmissions, clutch engagement and gear selection are tested. Braking performance is also checked under controlled simulated loads. This phase helps confirm that the powertrain, drivetrain, and braking systems are functioning exactly as intended before the vehicle ever touches pavement outside the plant. Following the rolling road, the vehicle undergoes an emissions and noise compliance check. In the emissions booth, exhaust gases are captured and analyzed by high-precision equipment to ensure they meet the regulatory standards of the destination market. For noise compliance, sound level meters measure exterior and sometimes interior noise levels under specified conditions, ensuring that they fall within acceptable limits for both legal compliance and customer comfort. With these mechanical verifications complete, attention shifts to fine detailing and final adjustments. At the fit and finish inspection stations, experienced workers examine every panel gap, every seam, and every interior surface for perfection. Door alignment, hood closure effort, and trunk latch operation are all tested. Inside the cabin, all switches, controls, lighting, and infotainment functions are checked one by one. Even the alignment of stitching on seat upholstery can be grounds for rework if it fails to meet the brand's aesthetic standards. One of the more dramatic quality checks is the water leak test. The Chevrolet is driven into a sealed booth equipped with high-pressure spray nozzles that douse the vehicle from all directions, simulating heavy rainfall and road spray conditions. After several minutes, the vehicle is opened and inspected for any trace of water inside. Any leak, no matter how minor, is immediately repaired, often by replacing seals or adjusting window or door fitment. Once the car passes the water test, it proceeds to the underbody inspection area. Here, the vehicle is lifted and technicians check for proper routing of hoses, cables, and exhaust components. Protective coatings are examined to ensure full coverage, especially in corrosion-prone areas such as wheel wells and chassis rails. This stage is also a final safeguard for identifying loose fasteners or missing clips. The last stage before leaving the assembly building is the final audit. This is a comprehensive evaluation combining visual, functional, and performance checks into one ultimate sign-off process. The audit team often includes some of the most experienced personnel in the plant, and their approval is a requirement before a car can be released. Every system, from headlights to climate control, is tested again, and any deviation from perfect operation is corrected immediately. Once signed off, the Chevrolet is prepared for shipment. Protective plastic films are applied to painted surfaces most vulnerable to transit damage, such as hoods, roofs, and door edges. The interior is covered with disposable mats, seat covers, and steering wheel wraps to keep it pristine until delivery. From here, the vehicle enters the shipping yard, where it is grouped with others bound for the same distribution points. Domestic-bound vehicles are loaded onto specialized car carrier trucks with wheel straps securing them in place. For longer domestic routes, some are shipped by rail in enclosed auto racks. Export vehicles are driven onto roll-on/roll-off ships for overseas transport, where they are secured in dense, organized rows for the voyage. Upon arrival at regional distribution centers or directly at dealerships, each Chevrolet undergoes a pre-delivery inspection to ensure that transport has not caused any damage or alignment issues. Fluids and tire pressures are rechecked and protective coverings are removed. If accessories ordered by the customer were not installed at the factory, they may be fitted at this stage. Only after this chain of precise manufacturing, rigorous testing, and careful transport does the vehicle reach the customer. From the initial design to the moment the keys are handed over, every Chevrolet is the product of thousands of coordinated actions, each performed to uphold the brand's standards of reliability, performance, and quality. Long before a Hyundai rolls out of a showroom or cruises down a highway, it begins life in a complex and highly synchronized industrial process that blends advanced automation with skilled human craftsmanship. The journey starts far from the factory floor, in Hyundai's design and engineering centers, where teams of stylists, mechanical engineers, safety experts, and manufacturing specialists collaborate to transform a concept into a buildable reality. This early collaboration is critical. It ensures that the car's shape, structure, and systems are not only aesthetically pleasing and mechanically sound, but also feasible to mass produce. Every curve of the body is analysed for how it will be stamped from metal sheets. Every bracket and mounting point is evaluated for efficient installation, and every wiring harness route is mapped to avoid interference with other systems. Hyundai applies design for manufacture principles from the outset, reducing assembly complexity and ensuring consistent quality. Once the design is finalized, the manufacturing engineering teams take over. Their task is to translate that design into a precise, step-by-step production plan that integrates seamlessly into Hyundai's global manufacturing network. This means specifying which machines, robotic systems, and fixtures will be required, how the assembly line will be arranged, and what level of automation each task demands. Many Hyundai plants are set up for mixed model production, allowing sedans, SUVs, and even electric vehicles to be built on the same line. This flexibility demands exceptionally detailed scheduling and tooling strategies. The process physically begins with the arrival of raw materials. The backbone of most Hyundai vehicles is steel, often high strength, and sometimes blended with lightweight aluminum alloys for weight savings. These materials arrive in the form of massive coils, each weighing several tons, delivered by rail or truck directly to the stamping plant. Before the first press stroke, these coils are unrolled, cut into flat blanks, and fed into enormous stamping presses. These presses are monumental machines capable of exerting thousands of tons of force. They shape the flat metal sheets into body panels, such as fenders, roof sections, hoods, and door skins. Each panel typically passes through a series of dies, the first forming a rough shape, the following ones refining it to exact tolerances. Hyundai's dies are precision engineered and often swapped out by automated die changing systems to minimize downtime between production runs. Dimensional accuracy at this stage is essential. Even a slight misalignment in a stamped panel can cause compounding fitment problems later. To prevent this, Hyundai employs automated vision systems and laser scanners that inspect each panel as it leaves the press. Any panel outside specification is sent for recycling, with the metal returned to the supply chain to minimize waste. From stamping, the panels move into the body shop, a vast, robot-dominated hall where the skeletal structure of the car is assembled. Here, the flat pieces are transformed into the three-dimensional form of the vehicle in a process known as body-in-white assembly. This stage is dominated by robotic spot welding, with articulated arms, moving in carefully choreographed sequences to fuse panels together at hundreds of points. The process starts with the floor pan, onto which side frames, roof rails, and bulkheads are positioned and clamped into place by large jigs. These jigs ensure precise alignment so that every vehicle matches the dimensional blueprint exactly. Additional reinforcements are added at structural stress points, such as the pillars between the doors and the crash-absorbing sections at the front and rear. Although robots do the majority of welding, skilled human operators remain essential in the body shop. They handle welds in areas where robotic arms cannot easily reach, inspect the quality of robotic welds, and make fine adjustments to ensure panel gaps and alignment stay within tolerances. In some Hyundai models, structural adhesives are applied alongside welds to increase rigidity and reduce noise, vibration, and harshness in the finished car. Once the body shell is fully welded, it undergoes a dimensional inspection. This involves laser measurement systems or coordinate measuring machines that scan key reference points to ensure that the body conforms to the exact design specifications. Any deviation, even as small as a millimeter, can lead to problems fitting doors, glass, or interior components later. When the body passes inspection, it proceeds to the paint shop, one of the most meticulously controlled environments in the entire factory. The paint process is highly sensitive to dust, humidity, and temperature, so the paint shop is sealed and climate controlled. Before painting begins, the body is cleaned and pre-treated in a series of immersion baths. These remove oils from stamping and welding, apply a corrosion-resistant phosphate layer, and prepare the surface for primer adhesion. Following pre-treatment, the body is submerged in an electrically charged primer bath in a process called electrophoretic deposition, or e-coating. This ensures that primer reaches even hidden cavities, providing a uniform anti-corrosion layer. The body is then baked in an oven to cure the coating into a hard, protective shell. Next comes surface preparation. Technicians and automated sanding units smooth the primed surface, removing any tiny imperfections. The body then enters the base coat booths, where robotic arms apply the vehicle's chosen color in ultra-fine, even layers. For certain models, multi-coat or two-tone paint schemes require masking and additional spray cycles. After the base coat, a clear coat is applied to give gloss and long-term UV and chemical resistance. Each coating layer is cured in a controlled temperature oven to ensure hardness and durability. When the body emerges from the paint shop, it looks like a complete vehicle from the outside. But it is still just a shell. No drivetrain, no interior, and no wiring. This is when it moves to the trim and chassis assembly areas, where it truly begins to take on life. The first steps in trim assembly involve installing insulation and wiring. Sheets of sound-deadening material are placed strategically in the floor, doors, and bulkhead areas to reduce road and engine noise. Pre-assembled wiring harnesses are then routed through the vehicle, connecting future components such as lights, sensors, the infotainment system, and power accessories. These harnesses are secured with clips and ties to prevent rattles and wear over years of use. While the wiring is being installed, HVAC ducting and other hidden systems are fitted. Then comes the dashboard, which often arrives as a complete module from a supplier. Installing the dash is a delicate process, requiring alignment with mounting points and simultaneous connection of numerous wiring plugs. After the dashboard, seats are installed, bolted into the floor, and connected to their respective power or heating controls if equipped. Meanwhile, in a separate section of the plant, chassis and drivetrain components are being assembled into a single underbody module. This includes the engine, transmission, front and rear suspension units, exhaust system, and sometimes the steering assembly. Hyundai uses modular assembly techniques so that this entire unit can be brought to the body in one coordinated step. That step is known as the marriage, and it is one of the most visually striking moments on the assembly line. The painted body shell is suspended slightly above the moving chassis unit, and then the two are lowered and joined together. Bolts are torqued to precise specifications, linking the engine, drivetrain, and suspension to the body. Once the marriage is complete, fluid lines, electrical connections, and control linkages are secured between the body and chassis. This is followed by glazing, installing the front and rear windshields and side windows. High-strength adhesives bond the glass to the frame, contributing to both structural rigidity and weather sealing. By this stage, the Hyundai is a complete, self-contained unit, but it must undergo rigorous testing, adjustment, and final detailing before it is ready to leave the factory. With the body and chassis joined and the major mechanical systems in place, the Hyundai enters the final stages of production. A series of detailed inspections, dynamic tests, and finishing touches that ensure it meets both regulatory standards and Hyundai's own quality benchmarks. This part of the process is just as critical as stamping or welding because it determines whether the car will leave the factory flawless or require rework. The first stop is often the wheel alignment station. Using laser-guided or camera-based systems, technicians check the vehicle's suspension geometry, ensuring that the camber, caster, and toe of each wheel match precise factory specifications. Proper alignment not only affects handling and stability, but also determines tire wear and fuel efficiency. Adjustments are made by trained workers using specialized tools, often within a tolerance of a fraction of a degree. From alignment, the vehicle moves to fluid fill and system pressurization. Even though some fluids, such as engine oil or coolant, may have been partially filled earlier in the assembly, this stage ensures all systems are topped to exact levels. The brake and clutch systems are bled of any trapped air, guaranteeing consistent pedal feel. The air conditioning system is charged with refrigerant, and the fuel system is pressurized to check for leaks. In hybrid or electric models, the high voltage battery systems are also energized and checked for correct function. One of the most significant milestones comes next: the first engine start. At a dedicated station, a technician initiates the ignition sequence or engages the start button. The powertrain roars or hums to life for the very first time. While this moment has a certain ceremonial feel, it is primarily a diagnostic test. Sensors and the onboard diagnostic system are immediately scanned for error codes, while technicians listen for any abnormal sounds and monitor idle stability. Any fault detected is addressed immediately before the car progresses. Following the initial start, the Hyundai is driven onto a rolling road dynamometer, a sophisticated test rig with large rollers beneath the wheels. Here, the vehicle's drivetrain is run through a series of simulated driving conditions. Technicians shift through gears, accelerate, decelerate, and brake, all while sensors record performance metrics. This test checks everything from transmission shift quality to ABS functionality. For electric and hybrid vehicles, regenerative braking performance is also verified. The dynamometer can simulate different road loads, allowing Hyundai to ensure the vehicle responds correctly in both light and heavy driving scenarios. Next, the vehicle enters an emissions and noise compliance station. The exhaust system is connected to high-precision analyzers that measure levels of pollutants such as carbon monoxide, hydrocarbons, and nitrogen oxides, ensuring compliance with the environmental regulations of the target market. Noise testing is also performed, measuring sound levels both outside and sometimes inside the cabin to confirm they meet legal and brand comfort standards. Once mechanical and emissions checks are complete, the Hyundai proceeds to the fit and finish inspection area. This is a zone where highly trained quality inspectors meticulously examine the car's exterior and interior for even the smallest imperfections. Panel gaps are measured with gauges, paint surfaces are inspected under bright, angled lighting to reveal any blemishes, and all interior features are tested for correct operation. If a trim piece is misaligned by even a millimeter, it is corrected on the spot. One of the most important tests at this stage is the water leak test. The car is driven into a sealed chamber fitted with high-pressure spray nozzles, which bombard it with water from all angles to simulate heavy rainfall and road spray. After several minutes, technicians open the doors, trunk, and hood to inspect for any signs of moisture inside. Leaks are unacceptable, so any that are found trigger immediate sealing repairs or component adjustments. Underbody inspection follows, with the vehicle lifted on a hoist so workers can check that exhaust systems, fuel lines, brake hoses, and electrical cables are correctly routed and securely fastened. Protective coatings applied earlier in the build are examined for complete coverage, especially in high corrosion areas like wheel wells and chassis cross members. The final audit is the last checkpoint before a Hyundai can be cleared for shipment. This audit is a condensed but highly rigorous version of all prior tests. Inspectors cycle through every electrical control, verify all lighting and warning systems, and ensure the climate control works in heating and cooling modes. They also test locking systems, window regulators, mirrors, infotainment units, and safety features like airbags through diagnostic systems. The goal is to confirm that the car leaving the factory is indistinguishable in quality from any other unit of the same model, regardless of production date. Once the final audit is passed, the car moves to the shipping preparation area. Protective films are applied to vulnerable painted surfaces, such as the hood, roof, and trunk lid, to guard against minor scratches or debris during transport. Interior surfaces, such as seats and steering wheels, are wrapped with disposable covers. The vehicles are then driven to the factory's dispatch yard, a vast parking area organized by destination. Here, they are scanned into Hyundai's logistics system using their unique vehicle identification numbers. This tracking system links each car to its market, dealer, and production details. Domestic shipments are typically loaded onto multi-deck car carrier trucks, secured with wheel straps to prevent movement. For longer domestic journeys, rail transport in enclosed auto racks may be used. Vehicles bound for export markets are moved to ports, where they are driven onto roll-on/roll-off ships. These massive vessels function like floating parking garages, with cars parked in tight formation and secured for the ocean voyage. Once at their destination country, the vehicles undergo customs clearance before heading to Hyundai's regional distribution centers. Here, a process called pre-delivery inspection, or PDI, is performed. This includes removing protective coverings, checking fluid levels and tire pressures, and confirming no damage occurred during transport. Any market-specific adjustments, such as headlight alignment or software settings, are made at this stage. From the distribution center, the cars are delivered to dealerships, where a final light inspection is carried out before they are placed on display or prepared for customer delivery. When the new owner takes the keys, the journey that began with raw steel coils and a concept drawing is complete. Though for Hyundai, the feedback loop from customer to factory continues, helping refine the next generation of vehicles. Before a Nissan vehicle ever reaches the open road, its story begins long before the first bolt is tightened or the first panel is painted. The creation of a Nissan car is a journey that blends advanced engineering, precision manufacturing, and human skill into a seamless, highly coordinated process. It begins in design studios and engineering departments, where the model is conceived, refined, and optimized for production. Design is never just about looks. For Nissan, every curve and contour is evaluated for aerodynamic efficiency, structural integrity, and manufacturability. Engineers work closely with manufacturing planners to ensure that the design can be built consistently at high volume. This process is called design for manufacturability, and it addresses questions like, can a panel be stamped without deforming? Can a wiring harness be installed without excessive labor time? Can a structural weld be made easily by a robot? These early decisions will determine the efficiency and quality of the factory floor operations months or even years later. Once the design is finalized, manufacturing engineering takes over. This is where the factory plan is built, specifying the sequence of operations, the type of machinery to be used, and the layout of the assembly line. Nissan's factories are often capable of building multiple models on the same line, which means the plan must account for mixed model production. In practice, this requires flexible tooling, quick change robotic programs, and precisely timed deliveries of parts so that the right components are always at the right station when a specific model arrives. The physical process starts with the arrival of raw materials, primarily steel and aluminum. These materials, often in the form of giant coils weighing several tons, are delivered by rail or truck to the plant's stamping facility. Before a single press stroke is made, the coils are unrolled, flattened, and cut into blanks, flat sheets of the correct size for the parts to be made. These blanks are then fed into huge stamping presses capable of exerting thousands of tons of force. Each body panel, whether it's a door skin, roof panel, fender, or hood, is formed by passing through several stages of dies. The first die forms the rough shape, while subsequent dies refine the panel, adding curves, ridges, and precise dimensions. The dies themselves are precision-engineered steel blocks that must be perfectly aligned and maintained to avoid defects. Quality checks start here. Robotic measuring arms or laser scanners inspect the panels for dimensional accuracy and surface quality. Even minor ripples or distortions can cause problems later during assembly, so any out-of-spec panels are removed from the line and sent for recycling. From stamping, the panels are moved into the body shop, a large, highly automated hall where the panels are welded together to form what is known as the body in white. This is the skeletal shell of the car before painting and assembly. Large jigs and fixtures hold panels in the exact position while robotic arms perform spot welds, fusing the metal together. In modern Nissan plants, robots handle the majority of welds, ensuring speed, repeatability, and strength. The process usually starts with the floor pan. Side panels, roof structures, and cross members are added in a carefully planned sequence to maximize rigidity and precision. Reinforcements for crash safety, such as high-strength steel beams in the doors and roof pillars, are installed at this stage. Doors may be temporarily hung for alignment checks, but are often removed later to make interior assembly easier. Although automation dominates, human workers remain essential. Some welds, especially in tight or complex areas, are better handled by skilled technicians. Workers also monitor the robotic systems, making adjustments when necessary and performing visual checks for weld integrity. When the body shell is complete, it undergoes a dimensional inspection using coordinate measuring machines or laser scanning systems. This ensures that the structure matches the precise dimensions required for later assembly steps, where mismatches can cause issues with panel fit or sealing. Next, the bare metal body heads to the paint shop, an area of the factory with the most stringent cleanliness requirements. Dust, dirt, and moisture can ruin a finish, so the paint shop is a sealed, climate-controlled environment. Before painting, the body goes through a series of pre-treatment baths to remove any residual oil or dirt from stamping and welding. These baths also apply a phosphate layer that improves corrosion resistance. After pre-treatment, the body undergoes electrophoretic deposition, or e-coating. In this process, the body is submerged in a primer bath where an electric charge causes the primer particles to bond evenly to the entire surface, including hidden cavities and seams. The coated body is then baked in an oven to cure the primer into a hard, protective layer. Once cured, the body is sanded to smooth the surface before the color coats are applied. Robotic sprayers, precisely programmed for each model and color, apply the base coat evenly over every contour. In some cases, human painters handle special finishes or complex two-tone applications. After the base coat, a clear coat is applied to provide gloss and protect against UV and environmental damage. Each coat is cured in an oven, hardening the finish and locking in the color. When the painted body emerges, it looks complete on the outside, but remains an empty shell. The next stage, trim and chassis assembly, is where the car starts to take shape as a functional vehicle. The first step in trim is installing sound deadening materials, insulation, and wiring harnesses. These harnesses, pre-assembled into model-specific layouts, are routed through the body and secured in place. HVAC ducting is fitted, followed by the dashboard, which usually arrives as a fully assembled unit from a supplier. Seats are bolted into place, carpet is laid, and door panels are installed. In parallel, the plant's chassis line is assembling the mechanical heart of the car. The engine, transmission, suspension assemblies, exhaust system, and brakes are mounted onto a subframe or separate underbody unit. This modular approach allows for rapid final assembly once the chassis and body are ready to be joined. The marriage process is one of the most striking moments in Nissan's assembly line. The painted body is suspended above the rolling chassis module, and the two are brought together by synchronized lifts. Bolts are torqued to specification, connecting the drivetrain and suspension to the body. Following the marriage, Technicians connect the various systems between body and chassis, electrical plugs, coolant hoses, fuel lines, steering linkages, and more. Windows are installed using high-strength adhesive, and exterior trim pieces such as weather strips, moldings, and badges are applied. At this point, the Nissan is a complete vehicle in form, but must still prove itself in function. The next phase, testing, inspection, and final adjustments, will determine whether it is ready for shipment to customers. With the major assembly work finished and the Nissan now standing as a complete vehicle, the factory's focus shifts toward verification, fine-tuning, and preparing it for the journey beyond the plant gates. This stage is not simply a final glance over the product. It is a comprehensive series of tests and inspections designed to ensure that every function operates exactly as intended and that the vehicle meets Nissan's rigorous quality standards as well as the legal requirements of its destination market. The first stop in this phase is usually the wheel alignment station. Here, precision laser or camera-based measurement systems determine the exact angles of each wheel relative to the chassis. Technicians adjust camber, caster, and toe to within factory specifications. A misalignment at this stage would not only affect handling and tire life, but could also cause warranty claims, so the process is handled with meticulous care. From there, the vehicle moves to the fluid fill and pressurization stage. While some fluids such as oil and coolant may have been partially filled earlier, this step ensures that all systems are fully charged to their specified capacities. Brake and clutch hydraulics are bled to remove any trapped air, guaranteeing a firm pedal feel. Air conditioning systems are charged with refrigerant. The fuel system is primed, and in hybrid or electric models, high voltage battery systems are energized and checked for correct operation. Each fill station uses automated metering systems to deliver exact volumes, minimizing waste and ensuring repeatability. One of the most anticipated moments comes next, the first engine start. At a dedicated station, the technician engages the ignition or push button start, bringing the Nissan's powertrain to life for the very first time. While this might appear ceremonial, it is primarily a diagnostic event. The vehicle's onboard computer is scanned for any fault codes, idle speed is observed, and technicians listen closely for any unusual noises or vibrations. If a warning light appears or a diagnostic scan reveals an error, the vehicle is diverted to a repair bay before continuing. Once the initial startup checks are complete, the Nissan moves to the rolling road, also called the chassis dynamometer. Here, the drive wheels rest on large rollers that simulate road resistance. A trained operator runs the vehicle through various speeds, load conditions, and gear changes, while onboard sensors and external instruments record performance. This stage verifies smooth transmission shifts, proper acceleration response, correct ABS function, and stability control operation. For electric and hybrid models, regenerative braking efficiency is also tested. Following the dynamic test, the vehicle enters the emissions and noise measurement booth. Exhaust gases are captured and analyzed to ensure compliance with the emissions regulations of the market the car is destined for, whether that's Europe, North America, or Asia. The booth may also include sound level monitoring to verify that engine and exhaust noise remain within acceptable limits. For some models, interior noise levels are also measured to maintain Nissan's comfort standards. With the drivetrain and emissions verified, the Nissan proceeds to the fit and finish inspection zone. This is a brightly lit area where experienced inspectors examine every exterior panel and interior surface. Panel gaps are measured to ensure uniformity, and paint is checked under angled lighting that reveals imperfections invisible in normal conditions. Inside, every control, switch, and display is operated to confirm proper function. HVAC systems are tested for both heating and cooling performance. Infotainment units are powered on and tested for audio quality, and safety features, such as seatbelt warning systems, are checked. One of the most critical functional tests is the water leak check. The car is driven into a sealed chamber fitted with high-pressure water nozzles that bombard it from all directions, simulating heavy rain or car wash conditions. After several minutes of soaking, technicians enter the vehicle to check for even the slightest signs of moisture. Any leak detected, whether from a window seal, door gasket, or body seam, results in immediate repair and retesting. Next comes the underbody inspection. The vehicle is lifted on a hoist so workers can examine fuel lines, brake hoses, exhaust components, and electrical wiring for correct routing and secure fastening. Protective coatings applied earlier in the build are checked to ensure they fully cover vulnerable areas, especially in regions prone to corrosion. This step also allows for one last visual confirmation that no tools, fasteners, or foreign objects have been left behind during assembly. The last in-plant checkpoint is the final audit. This is a comprehensive, multi-point inspection that serves as the ultimate quality gate before the vehicle is released for shipping. The audit team includes some of the most experienced inspectors in the plant, and their role is to verify that every system operates flawlessly. The process includes both static checks, such as lights, controls, and displays, and short, low-speed driving within the factory grounds to confirm steering feel, brake performance, and noise levels. When a Nissan passes the final audit, it is cleared for shipment. In the shipping preparation area, protective films are applied to painted surfaces most likely to be scuffed during transport, such as the hood, roof, and door edges. Interior surfaces like the seats, steering wheel, and carpets are wrapped with disposable covers. The cars are then driven to the factory's dispatch yard, where they are parked in organized rows according to their destination. Each vehicle is scanned into Nissan's logistics system using its unique vehicle identification number, linking it to production data, quality records, and shipping instructions. Domestic-bound cars are usually loaded onto multi-level car carrier trucks, with each vehicle secured using wheel straps or chocks to prevent movement. For longer inland journeys, rail transport in enclosed auto racks is sometimes used. Export vehicles are driven onto roll-on/roll-off ships, enormous vessels designed specifically for transporting thousands of cars at once. Inside the ship, the vehicles are parked in tight formation and secured with lashings to keep them stable during ocean crossings. When the ship reaches its destination port, Nissan vehicles are driven off and placed into secure holding areas for customs clearance. Once cleared, they are transported to regional distribution centers. Here, a process called pre-delivery inspection, or PDI, is carried out. Technicians remove transport protections, recheck fluids and tire pressures, confirm there is no transport-related damage, and make any market-specific adjustments, such as software updates or headlight aim changes. Finally, the vehicles are dispatched to dealerships, where a last brief inspection is done before placing them on the showroom floor or preparing them for immediate delivery to customers. The moment a buyer takes the keys marks the end of the manufacturing journey, but for Nissan, the process is part of a continuous loop. Feedback from customers and dealerships feeds back to engineering and manufacturing teams, influencing improvements for future models. The highlight of this stage is the marriage, when the body is lowered onto the chassis assembly. Using synchronized lifts, the two halves are brought together, and fasteners are torqued to precise specifications. At this point, the Chevrolet vehicle has its structural and mechanical systems fully united. From here, connections are made between the body and chassis systems. Electrical hookups, fluid lines, control linkages, and exhaust mounts are all secured. Windows are bonded into place with high-strength adhesives, exterior trim and badging are applied, and final adjustments are made to doors, hoods, and trunk lids to ensure perfect fit. and operation.